This episode is brought to you by Farm Bureau Financial Services, Zach Miller Agency. If you're looking for an insurance agent with a personal touch, someone willing to have the real conversations about what's important to you, assistance with submitting claims, and offering quality coverage options, Farm Bureau Financial Services, Zach Miller Agency may be the place for you. Whether you need home, auto, farm, commercial, life, or health insurance, we're here for you. Check us out at agentzachmiller.com. Farm Bureau Property and Casualty Insurance Company, Western Agriculture Insurance Company.
My next guest is a friend of the show and is our resident weather expert. Chase, thanks for making time to be here today.
Yeah, thanks for having me on again.
No problem. I'm Zach Miller with my co-host Vance Neidig. Good to meet you, Chase.
Hey.
And we are touching base with Chase Calkins again today. Welcome back to the show.
Yeah, thanks for having me on again.
No problem. You excited?
Yeah.
Nervous?
No, I usually do like one conference a year. I think last year I did 2 conferences, so I'm usually up in a giant auditorium in front of like 100 other people and just talking basically to myself, really. Because most of the people are just kind of like spaced out, because you can always kind of look down. They're always on like their phones, like, oh, I don't really care too much about like South American hail, or I'm just kind of here because I have to be, because my work hours are supposed to be during this time. Or they're trying to figure out, I was like, where am I going to go in a restaurant? Because like when we went to Virginia Beach last year, I think like one of the meetings went through to like 8 p.m. It's like, ooh, like, why would I do this conference from like 8 a.m. to like 8 p.m.?
Oof.
And so like the last session of the night, like everyone there is just like coming back with like a beer in their hand, and like everyone's just like having a fun time.
Yeah.
And so, yeah, these conferences, like the American Meteorological Society, which is the big one, that one was, I think 2 weeks ago. I didn't get to go to that one this past week, a couple weeks ago, but the other, I did it. Last year, that one was in Baltimore, and I think on the show last year, I came and talked, and Baltimore had just basically lost to the Chiefs, and the entire city was just kind of like depressed, but you didn't see anyone overturning vehicles or anything.
No fire started or nothing like that.
No.
Okay.
Not where I was at.
That's just Philadelphia.
Yeah. Yeah, because then I think even just a couple months after that, then that bridge collapsed.
Oh, yeah.
And from the airport, I actually I don't think I took the bridge over that bridge that collapsed. But yeah, and on the drive through, you can actually see the bridge that was there at that time, but it's not there anymore, obviously. But
They're starting to rebuild. I guess they wouldn't have been starting to rebuild by then, would they?
No. Because it was
still
still
cleaning
there.
up.
It was still there, and I don't know what they're doing with it now.
Mm-hmm. Interesting. So I realized after we did our first episode that it probably was not the best time for it to be having it without video, because we did a lot of speaking about things that were on our computer screen.
Right.
And so people were probably listening like, wish I could see what they were talking about.
I kind of went through that. I didn't listen to most of it, but I was like trying to follow along.
Yeah. Should be
trying to vision what you were talking about.
Yeah. Should be a lot more informative for the listeners this time. But how has life been otherwise since the last time you were on the show? I know you had a little bit of an addition to the family.
Yeah, my son was born May 15th. I always like telling the story because my wife never gets to probably let me down, because she started. We went to the doctor appointment, and they're like, "Oh, you're gonna check in, on the 15th at like 6 p.m. or something like that," and the hospital people wanted us there at 6 a.m., the doctors. And then hospital's like, no, you're going to come in at 6 p.m. And so we're, doing the last minute things where I, mow the lawn, get all the kids ready. And, they didn't want to make supper. So I went out and got Taco John's, and Layla's, just having difficulties. And, she's like, can you start timing me and everything? And so what's the thing is like, it's like 511. So it's like, go over 5 minutes for an hour, lasting a minute or something like that. And so I'm doing it. I'm doing the entire process, and it's lasting, the 5 minutes, but it's not lasting for exactly like 1 minute for an hour. It's like 45 seconds.
Right.
And so I was doing it like precise, and it got to be like at 11:30, we're like, we got to go like now. And so we drop off the kids at my mom's house. We get to the hospital at like 11:50. I was like, can we just like wait like another like 10, 15 minutes so we really don't have to get charged like this extra day for coming in for like these couple minutes. So, like no, we're not actually having this baby in this parking lot. And so yeah, we rush in, and the ladies are like, they see us and like, oh, you're basically like an active labor like now.
Yeah.
And so like they get the wheelchair, they rush us in there, and I'm just taking my sweet time, just like walking in there, like, close the door on me as I go up there. And I basically got like 12, I think I basically got hooked at like 12:05, and then like 12:15 is like when he was born. And because Layla was like, can I have the drugs? Like, I really want, like the thing is like, oh honey, we're way past
We're
this.
way past drugs. Yeah.
So like the doctor just like speeds there as like fast as he can. It's basically just like 1, 2, 3 done.
At least it was a quick birth.
Yeah, it was quick.
That's good.
Yeah, and compared to like Lincoln, where they make you stay there for like 2 or 3 days, like Norfolk is just like an express line. It's like, oh yeah, you had the baby. It's been 24 hours. You survive on your own.
Yeah, that sounds like the story we had with Declan when he was born. She was having some pains in the morning or the night. We went in the night before. She was having some pains, and they sent us home. She wasn't dilated enough. And the next morning, she's up pacing around. I'm like, you good? She's like, I just don't feel right. Next thing I know, she's like, I'm going to take a shower. And then she gets out of the shower, and she's just like leaning on everything, getting out. And I'm like, you good? She's like, I don't think so. So then we call the hospital, like, well, if she's not, whatever, don't worry about it. Go see the doctor. Get to the doctor. She gets all into the gown and on the table, and he takes one peek, and he's like, you need to go now. So they're like, all the nurses are scrambling around the office, trying to find a wheelchair, trying to get her in the wheelchair. I'm sprinting to the Tahoe to bring the Tahoe up. We get to the hospital. I'm going like 80 down 25th Street trying to get there. We get there, swing the doors open. They're already waiting outside for her with a wheelchair. They just kind of take her off. I'm like, okay, I guess I'll park the truck, whatever. So they already had her up in and everything. But by the time I got there, me and the doctor met at the elevator to go up.
Because Layla was like, should we take like a test run that way if we had to do this little crash course to just go through? It's like, no, it says like the sign like right there, emergency, go this way. I was like, okay. And so like we do it, and like I blow past the sign. And so I missed the turn.
Oh,
and so she's like, you missed it. I'm like, oh no.
You just got to remember it splits the buildings. Yeah. Good baby stories. That's fun. Anything else going on besides that? Had some shakeups at work, right? Or can you not talk about that? Or
no. So yeah, my company basically just kind of got bought out at like right after Thanksgiving. So the parent company is no longer like Verisk. Like we're now through Janus Research Group. They're, instead of us being based out of, I think Verisk was like New Jersey. Janus is through like Atlanta, Georgia, or one of the suburbs of there.
Okay. There's a lot of things in Atlanta. Isn't that where the CDC is?
I don't know. Maybe.
I think that's CDC headquarters. Sure. I'm pretty sure. And you guys do government contracts, right?
Right. So that's a majority of the stuff that we basically kind of do is we get government contracts. That's the initial reason why Janus wanted us was because I think like the space weather division, and there's something else that they kind of do.
There's space divisions that you said?
Yeah, there's space weather, and then there's the advanced technology division. Like they do stuff with like satellites. Like there's the Japanese satellites like Himawari that they do stuff with. I'm mostly kind of just like blank out during those like staff meetings because that's originally how I was hired, was for that advanced technology divisions where we did the stuff for off at Air Force Base, and you bring stuff from like the high side down to the low side, and then because that was basically kind of the main thing, because like what they were doing was basically kind of saying, here we have a 10-year climatology average for like AOD. Is basically how dirty is the atmosphere at, this certain point. And so on any given day, it's going to be like this. Well, they didn't want like it to basically do it as like a climatological record anymore. They want it to be kind of like an on-demand, so like a real-time kind of a product. And so we were kind of
see how dirty the atmosphere was?
Right.
Okay.
And so the North Grumman was in charge of like doing all the modeling stuff and basically getting that all up to speed. And I was tasked with basically kind of comparing it with like ground-based radars, the climatology, and basically how well the model did compared to before.
So is your company kind of like a smaller Northrop Lockheed type thing? Like
So
it's just a smaller group?
So like Northrop Grumman would basically kind of like hire us as like a subcontractor
Gotcha.
to do this kind of work.
Okay.
But now that Northrop Grumman lost the Seams 3 contract, because I think, what is it now?
That's been around for a long time. That was around when I was doing.
Yeah, because there was like Seams 1, Seams 2, Seams 3, and there's always been like continuations of it. And I forget what it's through now, but like SAIC won it. And the last I heard was like, they're not really happy with doing all that work for like SAIC. Like the science part is all kind of bad. And so I think like the government's kind of like pushed away from doing the science part with the SAIC. And I don't know, whenever they do like the next go round, if
Probably too much DEI.
like a lot of people I think jump ship from like Northrop to go to like SAIC because
They were an up and coming one, right?
Yeah, so the person that I replaced for AER, he was basically supposed to be like the main science person for SIC. And so he was supposed to do all this stuff. And after he got hired and was doing all this stuff, they basically said that, we don't want you doing that stuff. We want you to do something else. And so he quit. So they basically lost their like main science person. And I think that's basically kind of why it's not doing the greatest at the moment, because I don't think we're even doing anything. Like I think everyone is off base. I'm not even sure Mark is doing anything on base. I think he's off base. And we still had to have kind of like a satellite office, just kind of like having it around. But like we bought this office and then COVID hit.
I remember that you told that story.
And so like Mark was the one that used the office. And so it was basically just empty space. And so basically I kind of got like a two free tables out of it. Like I was using one of them, the other one's in my basement, still waiting for me to set up after, 2 years. So that way I can make an office for myself. But yeah, that office like shut down. So basically like everyone is like remote. So for like Nebraska, there's just 3 of us. So the other 2, Mark and Becky, are in Omaha, and here I am up in Norfolk.
Does each state have somebody? Or how does that go?
So I think there's a couple international people. I think there's one in like Germany. There's a New Mexico office for like Albuquerque. I think there's a Hampton, Virginia one. There's another remote person in Wisconsin. But otherwise, I think majority of people, like 85% are probably all in the Lexington office.
Do you have security clearance?
Yes, I have just the regular secret.
So you can go in, like, can you go on base?
No, because when you get like, when the Seams 3 contract expired and my work kind of expired, they make you give back your CAC. So I can't show up on the gate anymore and be like, oh, let me in. They usually would take your card and scan it and then say, go.
That's kind of sucks for you.
Yeah, I know, because you can't get like those like military discounts anymore.
Right.
Because I would be able to go to like a Quinta Inn, and I could basically say, since I'm a government contractor, you can get like leisure pricing or whatever. So you can get like the government rate.
Huh. Interesting. Is there any projects coming up that you might end up getting clearance again like that?
No, so you still get that clearance for like 10 years, and every 10 years it gets
to see like the files and stuff.
So it basically kind of like see those files. So like let's say that there was something for me to basically kind of like as a need to know basis is what they always like to say. So like if I were to basically see that project that I was working on, so it was on the high side, and so basically like imagine like all the top secret stuff is like behind that door right there.
Redacted.
Yeah. No, so it's like all on like computers, and so like you can't take any like electronic equipment with you. So like you have
of course you can. Yeah.
You have like your phone on you, and they're like, oh, if you have your phone on you, like stop, get up, get out, and set off to the side and stuff like that. So that way, just in case something was supposed to like happen, and so like
that's how Snowden happened. And
so like you can't like I can't even like plug my phone into like their Windows 7 machines,
right?
Because that's the thing with the government is they don't want to really update their system because it's like a whole huge headache, and
it's expensive.
I swear it was still like running on like Windows 7, and so like they would pay to basically kind of keep these things upgraded. So like,
I'm surprised it wasn't Vista or something.
Yeah, I don't think it was Vista. I think it was a Windows 7. But like I couldn't even connect to like the internet on base. Like we had to have
might have been XP then. Windows XP.
I can't remember.
It wasn't connecting to the internet.
No,
so I can't connect
on his phone.
Yeah, I couldn't use
couldn't.
I couldn't use the Air Force's like Wi-Fi.
Yeah.
So like we had to get like a little hotspot, And that's basically kind of like one of the reasons why they basically kind of made me be like work from home, because like Veris / or my company AAR would basically say, here's 15 gigabytes, worth of data. And I would blow that myself within just like a day. And so like each gigabyte is probably like an extra like $15. So like we were racking up like huge like data charges. So they're like, Chase, just stay at home and work.
Interesting. That's crazy. Do you want to get into some of this?
Sure. So like if you want to go to like those first like 2 images. So like there's one that's like the Hailcast one.
Of course it did that. I knew it was gonna. Hang on.
I'll put it in the other screen.
Okay. Which one do we look at first?
So we'll look at that like the Hailcast one.
The first one?
Yeah. So
This one?
yeah, that one. So basically what Hailcast is basically what you do is it's inside of Wharf, and it's like a numerical weather predictor. And so it's basically my boss Becky was basically the one that kind of designed it and added it into Wharf. And so it's basically saying, like here we want to basically kind of verify. So like this one was like a Hailcast event. So like in Colorado, this is like one of the biggest hail losses for Colorado. It was like a $2.3 billion loss for the state of Colorado just for this like one event. And so like, we model this and you can see basically where all this like red is where Hailcast is basically kind of saying that's, where 1 inch hail is falling. And so like during this time, I think like records of like 2 inches or more were even observed because it was just destroying buildings downtown in Denver. And so like the way that this kind of works is like you had this model. And so if I were to just show you this, this doesn't really mean anything to you. It's just a model. It could be this or it couldn't be. So what you need to do now is you need to kind of verify it. And that's what like the next image is self. So this is like the MRMS mesh data. And so this is basically radar data that's been, verified. It says, here's looking through the hail, this is what the maximum return is for like the maximum size of hail. And so like anything that's like purple is basically saying that, this is where 1 inch hail is going to more than likely be. So the way that this kind of works is like we separate it into like 1 by 1 grids. So basically say where each spot was, 1 inch hail, we would basically say we were verifying it that, Hailcast can detect hail in this, 1 by 1 grid box.
How big is that? How big of an area is that?
The 1 by 1 grid box? Ooh, I don't even know that.
So we don't know how like big this is, like just the Denver area or just Colorado?
This is just the one radar
Gotcha.
that's based out of, I think, Denver.
Gotcha.
But that's the corner, that's the panhandle of Nebraska, and that's Colorado.
Yep.
Those lines.
Oh,
That's
right
the
here.
actual map
Yes.
of Colorado.
Oh, gotcha. Okay. I didn't see that.
That's kind of what I was
Thanks for
assuming it was,
clarifying.
but I didn't know for sure.
You're right.
And then you got Kansas, Nebraska.
Yep, I see it
Wyoming.
now. Sometimes you got to spell things out for me. It's okay. So so what do you use these? Like, what can you use these for?
So originally what these is for, so we wanted to kind of like sell this data. So like this would be like interesting for you.
Insurance
or
company.
Insurance companies. And so basically kind of say is like, let's say that, I think this is on the podcast last time, let's say that I lived in, one of these 1 by 1 grid boxes.
Yeah.
And let's say that this 1 by 1 hail box gets more hail on average than, let's say, the one over it. So let's say it's twice more. Well, you're not going to charge the one person in this one box the same rate as like this other person. So we already know that this person more than likely sees like more hail. So, they're probably going to be seeing more wind damage, more hail instances with the roofs. And so that's basically kind of what it is, was basically kind of sell this to like insurance and make it for, money for the company. And so this original work was done and we were able to, get a company to buy it, but they weren't actually really interested in like the hail stuff to begin with. They were actually they wanted it for like wind, because that they wanted to get like wind plots off of like the ocean. Because what it is like, let's say that, you know, there's these stations along the coast, and this one station's worth like $100,000. This one down here is $80,000, and so on as it goes down the road. It's like, what is like, which one is actually more better to buy, or is it worth my money to spend more on the $100,000 one or the $80,000 one?
Mm-hmm.
And so that's what they kind of wanted to buy it for. But, you know, during this time we were able to get like a 20-year climatological record. But, you know, so like the work that I did, the one PowerPoint basically kind of led up to that. And
Okay.
so like if you go to that one,
Just got one question for you. So you did 20 years up until like a certain time frame
it was
and modeled it in the same area?
it not this area. So it's over CONUS. So
Okay.
when I say CONUS, it's over like, you know, basically the 48 states.
Okay. So you were able to, so you did this for the whole United States, basically, for the,
For the lower 48,
Lower
yeah,
48,
for 20 years. So I think it was like January 1st, you know, 2000 to, you know, December 31st, 2019, I think.
did you see quite a few patterns of it being in the same area, or did it move quite a bit?
Oh, so it moves seasonally, because like we were doing like even rain rates, and there was like solar radiance that you were wanting to look at. But for like hail, yeah, you basically kind of see like this pattern, and it's even in the one PowerPoint that
Which one is it?
the 20 AMS poster.
This one?
Yeah.
Swear to God, if it, oh, okay. It's like if it opens over there, I'm going to freak out.
Yeah, so this one you might kind of have to zoom in. So like when you go to these conferences, like these posters are massive. They're like 5 feet by like 6 feet or something like that. And it's on like a giant like poster board, and people like come up and see. And so like what this was is, you know, we're using Hailcast to basically produce like a dynamically downscale Hailcast hail climatology. And so you basically have like a 4 kilometer domain range. So it's like a really high resolution kind of model. And so, you know, basically kind of what this gets into is like, let's say that, so like in Norfolk it's, you know, there's like 25,000 people, and people will go through and they will submit like storm reports and say like, I was able to see like a 1-inch hail, and they'll submit it to like the National Weather Service or Storm Prediction Center. But if like you were to live out in the middle of like the country, and, you know, we do these severe thunderstorm warnings, and with these severe, I go to the left, because this is, we're basically talking about like population biases at this point. And so like here, I think that's part of Denver. I can't exactly remember which,
This
but
one?
yeah. So like these are like storm reports, and so like you can see like the population density, and so you can see like where it's more heavily populated, there's more storm reports compared to, you know, areas outside. So like major highways, like
Where people are going to be.
yeah, people are going to be. So you're
Yeah.
going to have more people, you know, doing it inside the city than probably, you know, Bob and Tom out in the middle of the country
Right.
doing like a storm report. And so, you know, because I even did this with the National Weather Service when I was an intern. They give you like a county record book, and you would call up where the severe thunderstorm was, and to basically verify your forecast. So we call these people and say, hey, we issued a severe thunderstorm warning. You know, one of the criteria is like, was there like 1-inch hail? Like, would you be able to like verify that for us? And, you know, most of the time these people are like not happy that you called them to begin with, because like, how did you get this number? Is this an unlisted number? And so like you just kind of like cross them off the book, like, don't call again. This person was like really pissed. and so like that's the entire point of this is like, so like if you were to go and like insure somebody out in like the middle of the country
Mm-hmm.
compared to somebody in the city, you
Right.
know, you can give it the same sort of overall record compared to, instead of like stating, you know, apples to apples instead of like apples to oranges, because you don't really know how hail is really affecting out in there. Because if you were to pull up the storm reports, it's like, oh, it doesn't really hail at that point that much, and so I'm not going to give them such a high insurance, you know, for their, you know, their roofs or their sidings, because it's not going to be. But if you were to actually have like radar data that says, you know, that says that it actually hails, and we actually are modeling it, And so then you can basically say everyone inside this box should basically kind of get like the same kind of rate or so.
Yeah.
And so you kind of go through, and so you can see go up, and so like and zoom in.
Which picture?
So like those 6 boxes, kind of
These 6 right here.
on the right. Yeah. So like here we're talking about Hailcast. Hailcast is on the left. You know, so we broke this down
So
into
those are actual hail events.
hail events. So the
Okay.
the one in the middle is actual real reports, or well, because Verus Respond is like an insurance company, is like their algorithm, how they said that there was hail or not.
Okay.
So like that would be like if State Farm had their own like weather team, or they had their own criteria or radar that says like, oh, this was hail at this point. And the mesh data is basically like the NOAA radars, and getting their maximum estimated size for the hail for like 1 inch. And so like you compare it for like those 3 years, for like April 2011 through 2013, and go against like Respond. And so you can kind of see on the right, like how much does it differ. So you can see that majority it's like within like 1 or 2 days. And then you can kind of see with the Hailcast, with the mesh, you know, like Arkansas is, you know, you're kind of over forecasting there in Arkansas. And so you can then scroll down, and then you can kind of see like the shift in the weather pattern. So like hail is now more located in the central panhandle, like Texas, Oklahoma region. And so you can kind of see the propagate there with the mesh. But then you kind of start to see there, you know, Verus Respond, you know, it does a little bit better. We're verifying it better with the Verus Respond compared to the mesh, because you're overestimating there with the mesh data. And the reason why we don't have Verus Respond for like those latter years is because that's all that Verus Respond was able to give to us, you know, I was able to get before they basically kicked us off that and said like, we're not going to share that data with you anymore.
Interesting. So this is like what actually happened, is what you're saying, the Verus Respond?
It's not that it technically happened. It's their hail algorithm that they developed for however they ingest radar data and give it such a threshold and say that it's going to be hail or not.
Interesting.
And then you kind of see here, then we propagate it through like June, and now it's more over like Nebraska. And like you kind of see that issue there with like a June down there for Florida. And that's kind of like an issue that we have right now with like the Hailcast is like the melting layer. And so we're really over forecasting there with the Florida, but then you kind of also see that we're under forecasting, you know, right against like the Rockies. And so like kind of like a terrain issue right there. So like with this is like only one single domain. And so like for us, if we wanted to kind of solve like these kind of like issues there along like the Denver region, since it's with the Rockies, what we would do is we would put like another domain within like that area to basically say that, you know, the terrain is like too complex. And so we can zoom in and put in, you know, more weather parameters. And that way it gives us like a higher resolution compared to just this 4 kilometer. So we could go to like maybe say like 1.3 kilometer resolution instead.
I didn't realize the Southeast got so much hail.
It's not, I mean, on average, yeah, it gets like hail, like I guess it's only 1 inch hail. But like if you're looking at the left one with like the Hailcasts, it's over forecasting because how it interprets like the melting layer. It's not like melting enough compared to where it's like supposed to be. So like Florida is generally kind of warm, and so it's not really melting like it's supposed to.
Interesting. Okay.
And so then you go over to like the right side. And so like these are like a area like under the curve. And it's like how well is like Hailcast doing overall? And so like what you want to do is you want to basically kind of like a straight line is basically kind of like a random guess. So if you're under that line, you're underperforming, and this one, if you're above the line, then you're overperforming, or you're verifying a lot better than what you're than, you know, just like a random guess. So in each of these years, we're basically, you know, doing a good job verifying it. And so the way that this was done is we took this radar data, and then we kind of, there's a grid that we kind of have to do where we do like Gaussian smoothing, and we regrid it to like a NCEP 211 grid. And so that's how this is kind of done. So it's not like a direct like Apple kind of thing. It's like one grid box to one grid box. It's smoothed out is the easy way to kind of describe it. And so then if you like go down, and this is what be like the reliability curves. And so here's where it kind of gets a little interesting, kind of confusing. So like in a perfect world, you would basically say this is where you want to kind of be like the straight line, where you're basically saying, if I say if it's going to be like 40% chance of like hail, is it 40% chance of hail? But so if you're under that line, then you are over forecasting. And if you're above the line, then you are under forecasting. So you want to be as close to that line as possible.
Interesting. It's fun stuff.
Yeah. And so, yeah, we got to do this a lot of times. So like even now, so like we did that 20-year record. We just got approved for this multi-million-dollar grant. It's called Ice Chip. And so in May, Becky and the other girl from like Wisconsin, they're going to travel to like, I think like Greenlee, like Colorado, and us and like a dozen different like universities are going to go out and basically kind of like chase hail. It's for like a better word, like, because it's a lot harder to kind of like track hail than it is to like say track like a thunderstorm or like a tornado kind of a thing.
Yeah.
And so like they'll go out. And I was doing some of these conferences, and like the cameras that they would do, like they have like cameras on like the back of the truck, and you can see like the hail as it like falls. The one of the things that we lost was the aircraft. I think it was like the King's Air, and it's based out of like Wyoming. And what it was planning on doing was it had like these little sensors. So the aircraft would go up and go through the thunderstorm, and they would drop these sensors, and the hail would accrete onto them. So you would basically see in real time like the formation of like hail. But that kind of cut from the budget. But otherwise, yeah, this is going to be like a 2-year project. So hopefully it hails during this time, because if it's not, then they're going to kind of cancel it and save the money for year 2 for like 26. So it'd be kind of disappointing if both years like we don't really get anything.
Yeah. It's probably a hard thing to predict, isn't it?
So that's where I come in. So that's basically I'll run the models and basically give the team that says, okay, you want to kind of like set up in this like target area. And so that way, when these storms develop, that they should be relatively close by.
What are the conditions for hail? What exactly needs to happen?
Let's see. You need.
Or is that a very broad question? I apologize.
It goes. There's a lot of kind of things that go into it. You need like a strong like.
I'll give you the dumb version.
You need a lot of upward forcing. You need a lot of like a super cold atmosphere for this, and so you want just like a lot of wind going up and down. So the way hail kind of works is like you have this updraft, and so like it just kind of like accretes and it goes up through the updrafts, and then it kind of falls down and it kind of goes up through the updraft again, and then
that's why it's so loud when it's in you can hear it in the clouds. Is what that is then? The
accretion is just
like when you say it goes up and then it falls down. Like I've always felt like you could hear the hail up in the clouds. Like it's a lot louder than like it's not really like thunder to me.
When I say like accretion, it's basically the growth of the hailstone, and so like it starts off a little tiny like kind of like a pebble. So you go like a pea size to like a nickel, a quarter, and it's basically how strong is that updraft to basically kind of keep that like single pebble up there for so long that
So like let it cook, basically.
yeah, kind of let it cook, that basically that it can get to, like, if you see like the pictures on the internet, it's like, oh, look at this hailstone, and you can see like all the different ends that kind of come off of it, and those are always kind of neat. And so you have to have like really strong updrafts, and I think it's somewhere around like 50 meters like per second or something like that, just to even kind of get like, I think it's like 1 inch of hail, and I think to get like 2 inches of hail, it's like 65 meters per second or something like that.
I always wondered how, like, because hail usually comes obviously in the like warmer time.
Yeah.
I just always wondered how that was possible, because it's basically like a ball of ice, right?
Yeah.
Yeah.
It's basically kind of like just like a frozen water molecule, and it just kind of gets stuck in an updraft, and it just, refreezes, and it melts a little bit, and then it refreezes.
Interesting. It always baffled me when it came to hail. I don't know why. It's raining ice in the summertime. Like it never hails in the wintertime.
No, it's like, because it's where like the freezing line is, like right now, if we were to kind of look at like the 500 millibars, this is like kind of like a good predictor. It says like, we are probably near like the 0 degree line. So if it were to basically fall as like snow, it should technically fall as all snow. But then there's like differences. So like rain, obviously it's above that melting layer. With like sleet, it like falls as snow, and like warms up a little bit, and it like refreezes.
Oh.
So like there's different kinds of different like precipitation that you can kind of get.
Yeah. I always wondered how all that was, I have no idea. You got to remember, I'm weather dumb. So some of the things you say are kind of going over my head, but I'm trying to ask questions without sounding too dumb over here.
Yeah, no, and that's always like kind of like the thing is like, we use our phones for like the weather. So like I could pull up my phone and I can pull up like the National Weather Service and say that, oh, it's going to be, let's say 30 degrees or something like that tomorrow. I don't actually know. And so like that's kind of like where I kind of like to come in and kind of like teach people like how to actually like where to kind of go for like the weather. And that's kind of like what I'm hoping to do, probably later. It's like that way you kind of can do it by yourself. So like, let's say that.
So you mean I can't text you anymore?
Oh, you can still text me because
Hey Chase, do I need to get in the basement or not?
yeah, that's always like my one thing is like that's the only time anyone ever texts me. It's like, hey, the clouds are kind of swirling. I still get a text from my mom. It's like, hey, did you see that the weather is bad? It's like, no, I forgot that I don't do that anymore for my job or anything like that.
Yeah.
So thanks for watching the weather for me.
We can do that right now if you want. If you want to tell us how to do all that.
Oh, sure. So
Unless there's something else you want to get into on this PowerPoint or whatever.
no, this PowerPoint's basically kind of like done.
Okay. Is there any other ones you want to talk about before you teach us how to do the weather?
No, nothing else is really
Weather related?
well. There's the SLS one. The machine learning one is just like turbulence.
This one?
Yeah, that's like turbulence.
Is that one we looked at last time too?
I think you looked at it, but of course, we didn't show it or anything, but I don't think you really kind of like understood or
I know.
no. And so like this is kind of like getting into like the AI kind of a thing now.
Uh-oh, AI, huh?
Yeah. And so like this is like the basis of like how it kind of works. And so like we have.
Can we show this on the podcast? Can we show it to the viewers?
Oh yeah.
Okay.
And so yeah, so this is like we have like it says, so we have like this business problem. So like this one, we were doing it was a cooperative research agreement with the Air Force that really kind of went south real fast because it's kind of like like you scratch me, I scratch you kind of a thing, but they didn't like really want to give us their like their data for like their aircraft. So I had to go out.
Of course not.
Yeah. And so I had to go out and get my own like aircraft data for, as it's flying through the atmosphere, like what are the weather readings. And so this is kind of like how it kind of goes. And so you have this problem and you kind of frame it up and you get the collection, integration, preparation, and you get the visualization. And you go through this future engineering and, tuning and whatnot. And so like once you run it all through this stuff, is the bonus, is the goals met or not? Yes or no? And so if it is, then you go to like the deployment, and then you get like these initial predictions. And so then this is kind of like where the machine learning kind of kicks in. This is where you basically give it all these different random parameters and make it do all these different things by just like tiny little differences to basically say to see if it gets any better or not. And so like the next page. So yeah, that's all. I know that you guys probably don't really care about this. Like, this is where I got like the data, it's
You'd
reported.
be surprised. We care.
So yeah, and that's always like the thing that I like to teach everyone is like, this is like stuff that you can technically like do by yourself. So like that those like wharf simulations, you can do that yourself. You don't like the way that I do it. Those are all like done on like AWS, and you're using just like a whole bunch of like processors to like do these simulations. So like if you can set up your desktop to use the different processors, you can do this like yourself. You don't need an Intel processor. Obviously, having an Intel processor really helps. You can just do this with the regular new processor and set it up. It probably just won't be as fast as what you would do. So you can technically do all this stuff yourself. Even the stuff later, the ski chem stuff, which I'll talk about. You can do that yourself. The company gives you everything that you technically need to do these simulations.
Interesting.
So like these variables that you get, you get the max EDR, which is the eddy dissipation rate, where the aircraft is, latitude, longitude, altitude, all these different things. And so we evaluate the EDR against all these different metrics. And so, we go down, because originally when I presented this, we used the ERAI, and that data was, just 3/4 by 3/4 degree resolution. And when I did this, the new data came out, which is the ERA 5, and so that's 1/4 by 1/4. So you can you'll see in the graphics that the training stuff gets a little bit better. And so this basically kind of says, what we kind of use. We use the ERA 5 over such a domain. With this, ERA 5, it only had 37 levels. The ERA 5 has 137 atmospheric levels. And so when we mean by atmospheric levels, we typically go through like pressure. So like if we say here at the surface, it's like, like 1,000 millibars or 1,013 millibars. That's surface. And so like, you look at your clouds and stuff like that, that'd be kind of like the 850, 700 millibar kind of level that you have. Then you have like your jets. Those are at like your 200, 300 millibar levels. And so when we do these levels, it's with the pressure levels, it's even across the entire globe. So if you were to do kind of like a surface at like Denver, Colorado, you would know that, there is no like 1,000 millibar level for like Denver. It's, closer to like 850. So like when you do these with atmospheric levels, you have more concentrated levels that are like near the surface and kind of differentiate through the atmosphere and get kind of lower. And so then you can kind of solve these and get heights out of them by using kind of like the hypnosymmetric equation. So you convert geopotential height to just regular height. And so that's kind of like what we did here, using like the radius of the Earth and gravity acceleration and exactly where it's at within respect to latitude and longitude.
There's a radius on the Earth. We're not flat.
Yeah, so
I was going to say that too. I knew you were going to.
Because of what it's roughly like 6,371 kilometers or something like that.
So in this study, did you guys figure out that where people could avoid turbulence?
Right. So what this basically goes through is, as these airplanes are flying through, like, because there's already kind of like we call them tabs. So these tabs are basically kind of used to basically say, even like the Norfolk Airport, they get tabs from like the National Weather Service in Valley, and it basically says, these terminal aerodrome forecasts, I think is what it stands for. TAF, terminal aerodrome forecast, and basically kind of says, like the clouds are at this level, winds at this, it might rain, there's flight visibility rules that could be in effect at this time. And so we can model then like where like these areas of like turbulence could basically kind of be. And so, through here, we kind of look at, aircraft that is flying below 10,000 feet or above 10,000 feet and how many points we kind of really get. And so you're going to have like more turbulence kind of like with the less than 10,000 feet because that's kind of like your landing and your takeoff.
Takeoff.
My goodness, I can't even think. It was like, what happens when a plane goes up? What is that called?
Levitates.
Yeah,
Chris Angel flight.
Yeah, so we kind of wanted to simulate as the plane's like flying through the atmosphere, like where turbulence is kind of be. So, go through. And so like here we are, we're kind of like estimating like an aircraft size. So here, these EDR thresholds. So like we're gonna say for like a medium aircraft, we're gonna set a threshold of like 44. And so these are like unitless. And so like a medium aircraft. So like I said, you got like a 737 going through it. And so that's the threshold. So like the first thing that we'll show is like a binary. So it's like a yes or a no kind of thing. So the next slide. Oh, and so like this is like kind of cool. This is called like a scatter matrix, and it shows us how each variable is correlated with each other. So like the red boxes, we can see that these two, they're highly correlated. What is that? It's vertical velocity. I think it's like vertical ETA. I think is like the other thing. So like what we'll do, we choose to remove ETA, coordinate, vertical velocity. So those two basically kind of the same kind of thing. So you can see how like temperature is like related to like wind speeds or vertical velocity divergence, the U wind, V wind. And so you kind of look for like patterns in these. And so that's kind of what you train the model to kind of do as well.
So those are all pieces of turbulence that could possibly be different types of it? Or
it's how like each variable is co-located to like everything. So with like, this is taking, you evaluate it on the eddy dissipation rate and how each of those kind of correlate with each other.
What is the eddy dissipation rate?
Oh, it's been so many years since I even had to even think about that. But I think it's just like
Google it?
I think it's just like the motion, like a sudden motion. I forget.
Of like the air?
Yeah.
Gotcha. Off of the object? Is that what you're saying? Or just air in itself?
A measurement of atmospheric turbulence intensity. It is used in aviation to predict the decay of aircraft wake vortices and to define clear air turbulence parameters. That's the definition I got from AI.
Oh, from the Google AI.
Yeah. So I'm just fascinated by these different pieces. Like the middle box that's going down looks like Tetris, and then
those are just like histograms.
You look like spray paint, and then you look like you got sound waves to the right and the bottom.
Yeah. So like if you, as we go through this, you'll see that some of these things may not mean anything at all.
Oh. Okay. You want me to keep going?
Yeah.
Okay.
And so, so like here you can see there's like 1-to-1. And so like here you can see like specific humidity with like temperature K, those things are kind of correlated with each other, but everything else, there's kind of like a negative kind of, or at least there's no weight. So you kind of want it to kind of be, highly correlated or highly uncorrelated. That way you have, these parameters that you want to either keep
so
or
keep
remove.
it or throw them out.
Yeah.
So like your ones, your greens is something you want to look for.
So like those, like when you look at it, so like the very first thing that you see is temperature K, and then the bottom is temperature K. So when you evaluate temperature K versus temperature K, you're getting like a 1-to-1 ratio. So
Yep.
when you look at like temperature K and specific humidity, you get like a 76% correlation. Temperature K with vertical velocity, that's basically 0. Temperature K divergence 0. U wind is negative.
Oh, now I see that. I wasn't catching that before. Okay. See, Vance is the math guy. He can read these real fast. We're good. Go ahead. Sorry. We're just pointing out my dumbness.
Yeah, so like there's the frontogenesis versus the L rod. Like there's those things that are kind of correlated there as well. So then we'll go through
More?
And so what we then do is we do this like supervised learning. And so like we classify these as being binary or multi-class. So the first thing we'll show is binary, and then we'll kind of get into like a multi-class. And then we're going to use like the XG boost that like AWS had.
Amazon?
Yeah.
You just gotta let me know when you want to keep going.
Oh, yeah. Next slide.
Okay.
And so, so like here's like the basics. You basically kind of create this XG boost container. You set the data for training and validation. We do everything. These storage containers. So like if you were to do like a directory, like it's called like an S3 bucket and like on AWS, you define the training parameters. How big of an instance or how fast do you want this to do? Define hyperparameters and the fit. And the only thing that you want to pay for is just the time that you want to train the model. And so like you go through like the next slide. And so like what is like these different hyperparameters that we use? Like there's like max depth. So like this is like the depth of the tree used to control overfitting, such as higher depth will allow model to learn relationships very specific to a particular sample. So like that's where you're kind of getting into like with the, let's say like temperature K and all those different other different variables, and the ETA, which is like the learning rate, and how many rounds are you going to be doing this for? So like if you do like 100 or 1,000 rounds, is there going to be any advantage or anything that you gain if you go from like 100 to like 1,000 or something like that?
So if you miss one piece of data given to this model, you screw the whole thing up.
As kind of like a initial guess, kind of, yeah, but then that's where like a second kind of is where like
that's why you wouldn't want to go like a 1,000 rounds right off the bat.
Yeah, so you can kind of like do like a small round, and you can kind of toy around with like all these different parameters. So you get like the best guess to begin with, and then you go through for like another 100 rounds and say, change these things by such a small. So you give it to kind of like a range, and so like let's say one variable is like from like 1 to 10 or something like that, and one sample will choose like 1, the next sample will choose like a 5, and it's just random. It's random choice basically.
How much? I mean, so Amazon Web Services is being used by like Amazon goes down, their servers go down. Like
there's different regions. There's a whole bunch of different regions.
I know, but still, they're AWS is used by a lot of different things.
And when you think of like all these different like servers and things that they have. The way that it was kind of explained to me is, they basically just have like giant like server rooms, and then they kind of
server farms, yeah.
And they kind of know when like one of these systems is going to kind of fail, and so like they'll take off that one system, change it out before it like completely fails, and you have kind of like a battery issue.
Yeah. 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 You want me to keep going on this?
Yeah. And so here, this is where I can kind of have you guys kind of look into it. Like, can you yourselves look at this and kind of see if there's any sort of like pattern? Like, how would you draw like the pattern of this?
How would I draw it?
Yeah, like if you were to basically say like where is like kind of like the average, or how would you say like
it's a little bit flat, but on an upward trajectory a little bit.
It's kind of like a U shape.
That's what I was gonna say. Yeah.
So then, if you go down to like the next slide,
are those all the same color?
Purple.
Is it all the same one color?
Yeah.
God, my eyes are so screwed.
And so so like here, like I was saying, like the human identified, we can see that it's kind of the green line. We can see it's kind of like a U shape. But then when you talk and you bring in like computers into it, this is kind of where the AI kind of comes in. Is like it doesn't know where it needs to kind of start. Does it start low and then it kind of goes up high, or up high and it comes on low? And that's the entire thing of the hyperparameter tuning is trying to find like the best kind of fit overall for these kind of things, because the computer doesn't. It just sees numbers. It doesn't know anything that's correlating between this.
Like
so,
I would
so the
look
computer's
at it
dumb.
closer to like that pink line is how I was visioning it, kind of throwing out these up here because it doesn't match anything else. That's kind of the way I looked at it.
The green one's kind of a Nike swoosh.
There you go.
There we go. Keep going.
Yeah. And so like how these kind of things, so you put on like these loss functions, and so like you had the starting point, and you basically have like these number of rounds, and so you kind of want to get down to where this minimum is. And this is kind of like where you don't want to like overshoot or anything. So like that's where like the next image is like a starting point, the next point. And so like you were to go down, you could potentially like overshoot. So like if you do two small steps, you can get there, but it takes a lot more data and time to kind of reach that minimum. But if you take these bigger steps, you can go down, you hit the minimum, but then like let's say your next step is like way up. Well, then you kind of like overshot and you kind of like ruined your like forecast. So yeah, next slide. Yeah, so yeah, this is what I was just kind of talking about. So like you take two big steps, you find the minimum, and then your next step is kind of like over it. So eventually the minimum is approximated with enough of these operations have been performed to determine, the weight of the results in the least amount of loss. So, next slide. Yeah, so this gets into, I kind of got ahead of myself with the overfitting and underfitting. So yeah, so like the one, like I said, is on the left, you overshot it, you didn't find the minimum, and the one on the right, you ran out of time, you didn't find the minimum. That's basically what these two are kind of saying.
So you got to find that.
You want to find that sweet spot at the minimum.
Okay.
And so how this...
But so kind of go back to that other one. If you did overshoot it, you would just reverse.
No, it wouldn't reverse. So like you've already overshot it. So like kind of like at that point, it just kind of like bounces back and forth.
So you have to start over?
It's not really so much as like starting over. It's just it couldn't find it. So
then what?
It just kind of tells it to...
It's going to assume that that's your lowest point because you've overshot it.
Well,
it's just going to go right back.
Well, because you found a low point and then you overshot it. So then what it's going to kind of do is it just kind of goes back again. So like you're taking more time to kind of try to find that low point.
So it'll figure it out. It just takes
it
more
might
time.
figure it out. It
might.
Yeah, that's always the thing with these AIs. It's like
so it could be completely screwed.
Yeah. And so like that's what when you do like these numbers around. So like if you do these 100 different simulations, let's say like half of them like you might overshoot it, or like a quarter of them you might run out of time, and maybe 25 of them were actually kind of usable or were better. And so that's kind of like what we kind of do.
And you got to thumb through all that data?
Yes. Oh, it tells me, like which one is the best technically on the website. It says, whatever run 38 or something like that was like the best run to give you like the best area under the curve or best accuracy. And so you go through and look at the different parameters. And then if you want to do it again, you can basically say, here's our starting point, and then you can do it again. But, this is just kind of like a quick kind of thing for like the Air Force.
Okay.
So then so what you do is like, let's say you have like 100,000 points. And so you basically set like 80% of that off to like train the model. So like 80,000 points, then use 10% of that to validate it, and 10% to test it. And, you basically kind of get these things like a random seed. And so it kind of jumbles up all the data. So that way, data sets 1 through 2, 3, 4, 5, they're not all like together. It's, 1, 5, 15. And so like if I were to give this thing like a different random number, it could be, different results. And so like how does this kind of work? We create like an endpoint and we reformat and load our data to create these predictions. And so basically how these kind of things are is like we evaluate on this confusion matrix. And so we predict true and is it true? So you get like a true negative, predict yes, actual yes, that's a true positive. Those are the two that you really want to see. You don't want to predict yes and it's actually a no, or it's predicted no and it's an actually yes. You want to stay within the orange and not the yellows.
Okay.
All right, so like here's kind of like we ran through this data set, and so here we can see like the accuracy is like roughly on like 69%. I kind of
Is that good?
as like kind of like a beginning point, like 69%. Area under the curve. You go back to like that one image that we were showing with the Hailcast. This is like 66%, I think, with like the Hailcast. Those were like 89% or something like that.
Okay.
And here's all these different scores that you see. So like, if it's for being severe, we predict, 211 cases as being true yeses, 1,500 cases as being true negatives. We're, predicting no, but it's actually yes, about 600 times, and predicted yes, and it's actually no, like 166 times. So here's like our starting point. And so now we'll take this data and we'll kind of like hypertune it and go through it again. Oh, so this is like the previous data. So this is with the ERAI. And as you can see, it's basically kind of a straight line. So when we did this before, like initially to show this with the government, the Air Force, there's basically no confidence within this stuff. So then if we, with the new data set that we were able to show, which should be the next slide. Yeah, so you can see how great it's able to improve with just like that resolution increase. So like the ERA5 was like a 3/4 by 3/4, and the ERA5 is like a 1/4 by 1/4. So you get more data within like those points. And so this is basically just saying yes or no for like a severe or extreme event. So so we said before, it's basically like a 66%, accuracy. And so that's basically what it's kind of showing. So then if we scroll down, so here we're doing our hypertuning parameters. And so you can see that, from before, we were at like 211 and 1,500. So we increased, those predictions. We decreased our true negatives, our false negatives go down, but then, we also kind of see some false positives kind of pop up as well. But the main thing is, we see that true positives being increased. So we were able to actually say that this is, like slightly better compared to before. And so you'll see that like on the next slide with this is that tuning thing that I was talking about. So it basically kind of tells me, those variables that I showed before, temperature K, specific humidity, vertical velocity, there on the bottom basically says, what was like the more driving factors within this eddy dissipation rate. So like the very first feature importance was this gradient GRN, which is gradient Richardson number. And then it's relative vorticity, divergence, the U wind, vertical velocity, U wind, temperature, and whatnot. So like time of day didn't really matter. LROD or specific humidity was like, like the worst one. And so like specific humidity was like so bad that, we should be able to remove it and also kind of like increase our chances. So like the next slide. Yeah. So this is just showing that, we were able to increase our forecasting as like before. So like the hypertuning was able to like increase it. It's not a whole lot better, but it's better. And, for a government, just a little bit of, better is really good enough for them at this point.
So with going these numbers, does that mean that those were the things that were going to make turbulence, or that was just the things that were giving
like
you the
the
best
weight.
data?
Like the weight.
Okay.
And so like this is just saying like how well this is kind of doing, and you kind of want this to be in the upper right hand corner. And so what do we have? We have like the success ratio versus the probability of detection. So we have a good success score, but the probability of detection isn't the greatest. So our critical success index, we're basically at like a 10% or so. So it's slightly better than our, random guess, but the hypertune's better. But like in this case, it's not, even it's not that great.
So they didn't want to use it, I'm guessing.
It's not that the original point of doing AI in this project was clouds for the Air Force. Was basically say, clouds are supposed to be here. Can I have AI? Basically, can I remove this person? She's going to be retiring. And can I have this model do it for me as well and save money and not have to pay this person a lot of money to manually put in these clouds that are supposed to be there, or I can pay, Amazon to kind of do it for me. And, they just kind of wanted to see how this machine learning kind of worked. And so that's kind of what this research cooperative agreement was. And they kind of wanted to go through it with this turbulence. But like I said, like they didn't give us the data and they kind of broke the agreement. And so we broke off the agreement with them. So then, that one before. So we removed those features, that specific humidity. And so then you see it did kind of increase just slightly because I think it went from like 69% to basically 70%. So you're able to put more weight on those other factors. So that's why we can, sometimes look at it and say, this parameter wasn't that great. So we can drop it, rerun it, and it just slight increase. So just all the kind of different things that you kind of do with these AI tuning tools. And so I think, is that the last of the binary stuff? Yeah. So basically kind of like the same image where it says, we're able to have a success ratio really well, but we're not detecting them the great. So our critical success rate index isn't the greatest. All right. So now we get into like these multi-class classifications. So this is where it kind of gets a little screwy. And so this is where we're actually trying to say, can I identify null turbulence or light turbulence, moderate, severe, or extreme? So can I nail down exactly what classification of turbulence there's going to be?
Okay.
And so as we go through, we kind of break these things up. So like 36% of the data is going to be null, light 25%, mediums 23, severe 17, extreme is like that 1.2%. So that's how we kind of broke all that down. And so like these are like the hyperparameter things that we have. So like like a max depth of like 5 different branches, this ETA of like 0.2, and all these different parameters that you can kind of put in. But like the main thing is like the objective, which is called the multi softmax. So that way you're getting like those 5 classes, and we're gonna do like the 100 different simulations. Okay. And so like this is how it's kind of like broken down. And so you see here, our null area, we're not doing the greatest, neither with the light, but we're doing all right with, the medium, severe, and extreme. But like overall, if we were to basically kind of combine this all into like one kind of unit, it's basically like a 54%, like accuracy.
Okay. So
it's better. It's slightly better than just like a best guess kind of a thing.
Okay.
And so then, now we basically kind of hyper tune it. We put in, like these better values that we think, that was based off of. Run through it again, and next slide. And we can see that it's still kind of like the same, but it kind of goes, slightly up. And so the multi-class is, kind of like a difficult. So like in this case, it's a lot easier to say yes or no than it is to basically categorize each of these different instances.
Whether it's going to be light or
And so this is just kind of like a kind of conclusion kind of thing. It says, like what are the best practices? And so like this is like what we were kind of trying to do, or what my next step was hoping to kind of do is basically kind of create like these maps that kind of say, like this is the region that you'll see like light and medium and the heavy turbulence. So kind of like avoid these areas.
Not too many severes on there.
No. Like for that one day, there's just, like a medium or so.
Interesting.
For like Kentucky.
Is that it?
Yeah, that's it for the AWS stuff. So like, so now we can get into like kind of like the weather stuff that I kind of like doing.
Okay.
So
is that this thing?
Yeah, it's this thing. So what I like to use is like the pivotal weather. So like people like they can go on their phones and they can see, like the
Weather
national.
bug.
Oh, yeah. You use WeatherBug? Is that what you
Just to check the temperature.
Oh, what do you use there, Vance? Did you?
Whatever's on my phone.
Probably
I think-
AccuWeather.
I think AccuWeather is. I usually only use it just to know what the temperature is going to be, and then I'll check the radar. That's all I ever really look at.
Oh, because I like using AccuWeather because if you
I
go
think
on,
it's AccuWeather.
if you go on AccuWeather, like AccuWeather will give you like a 3-month like forecast, so it can tell me, like on March 27th, it'll be like 60 degrees or something like that.
Apparently, it's not AccuWeather. It goes to the Weather Channel. No, weather.com is what it. I think I used to have AccuWeather on my phone, but I no longer have it.
So yeah, so like that's the main thing that people use is like the Weather Channel, but the Weather Channel anymore is kind of like a reality TV show where they have people go on and do like storm chasing or severe weather events and stuff. Kind of like
I
that.
like to wake up surprised.
It's not what it used to be. It used to just be the ticker and it'd show you the forecast and
Yeah, I don't even know if
to
you.
be surprised. Yeah.
I don't even know if you get like the local on the 8s anymore.
I don't know.
Like I can't
I
remember the
don't
last time
watch
I
it.
looked at the Weather Channel because
I don't even know if we have the Weather Channel on we have YouTube TV. I don't even know if it's on there.
yeah, I
I
don't,
couldn't tell.
yeah,
If it,
I don't believe it is on there because I don't even know. I have people who have like the local channels, like if they have
No.
like
Everybody's got it
I
on their
know.
phone now.
yeah, I know, yeah, and so this is what I kind of like to do is kind of like show people like the weather. So like people are like interested in like hail, like
But you paid for this, right?
yeah. So you can and you can't. So if you pay, you get like a zoomed in state level. So like if you like, where's the mouse? I'll take the mouse. Instead of saying like, Zach, click on this model, click on zoom,
There you
do
go.
all this stuff like really fast.
Just don't leave the screen.
All right. So like it's really easy. So kind of go through like a loop. And so we can kind of go through here. If we want to go through like local level, so like Nebraska. Oh, so here's our great state of Nebraska. And so like I was talking before, so like here's our precipitation rate. Here's our 1,500 millibar thickness. So anything
Can
that
you explain the millibar real fast? You said that like 20 times.
so like the millibar is basically kind of like the surface. So 1,000 millibars is basically our surface, and 500 millibars is kind of like in between like the clouds and the jet and stuff like that.
Okay.
So it's like where you kind of see like this is like heights that we kind of use for like weather.
so
Okay.
when he's, I think he's asking what a millibar is.
Oh,
like a measure, like it's a measurement. Is it? It's a pressure per
Yeah, it's a pressure.
like per square inch type
So,
thing. Like
So like
pounds
is
per
lower
square-
higher?
So lower, like if you have like a low pressure system, like a hurricane, stuff like that, that's like less than like 1,000.
Okay.
So like if you have like
So it's not distance, it's pressure. So it's where the pressure is.
yeah.
Okay. That makes more sense now. Thank you for clearing that up in my brain.
And so like these are basically just like heights. So like here you see like these red lines. So this is basically kind of going to show you like anything that's in this red area here should basically fall as rain. Anything here in the blue, if there is blue, yeah. So like here should be like snow or sleet, because this is basically kind of like our 0 degree line at this point. And so we can. I hate the GFS because it's terrible. So we'll go to like the ECMWF. I don't like 18Z because 0 and 12 is basically when we get like all of our like real time data. Like the 6 and 18 are kind of just like merging of like the two. So if you want to look at like real data, you want to go through like 0 and 18Z or 0 and 12Z.
Okay.
And so, do you know what Z is?
Nope.
Like, sure, if you were in the military, you would know. So like, it's like Zulu time. So like 12Z. So this is, this was valid at like 6.
Oh, so that's time.
Oh, it's just military time?
Yeah.
Oh, yeah. Okay.
Yeah. So like this forecast.
So this is based off of 24. It's your 24-hour clock.
Yeah.
Okay. So 12Z would be noon.
12Z is, so you have to subtract 6 because it's UTC, Central Time Zone. Well, Central Standard Time, since what we're now is UTC minus 6. So it'd be 12 minus 6. So this would be
6 a.m.?
6 a.m.
Okay.
And so you kind of go through here. So you can kind of see like what is like the weather going to be kind of like for like the week. And so like we'll play this and you can see how fast it moves. And so you can see like, oh, you're going to be seeing some like cold air kind of come through. There should be like a couple of like systems here that kind of like move through.
Okay, explain the lines again. So anything above the blue line
Yeah, so
could be snow.
So like right here is basically kind of like our 0 degree. It's like the freezing line. So anything down here should basically kind of be like rain. Anything up here should basically be like snow. So like Sioux Falls, you'll see up here. So like if I were to click on this, Sioux Falls. So here, this is called like a skew T. So you can see that, you know, you probably guys don't probably really understand this, but like here at the surface, you know,
That's what you're here for.
What we have here is, you know, the red line is our temperature and the green line is our dew points. So, you know, it's going to say at the ground level at that time, you know, it's going to be 20 degrees. And so you see these two lines like touching. So it's going to basically, what that tells you is like that entire column of air is basically moist. So you're going to be looking at like clouds. And so anything up here, kind of like the troposphere, stuff like that, stratosphere, you're going to have like just clear. So like this is where like the jet's kind of at. So you'll have like clear.
That's why it could be raining below where you're flying and be clear as day above you, or where you're flying at.
Yeah, because usually, what is it? You're flying right around what?
30,000 feet.
Yeah, 30,000 feet.
Hmm.
So you kind of want to. I think usually you want to catch like the jet. So you're usually flying somewhere in like this area here.
Interesting.
But then, like you have like all these different parameters. So like let's say that it is summertime, and let's say we're expecting like hail or thunderstorm or tornado. Let's say. So like we have these parameters called like CAPE, SIN, the LCL, lifting index, little free conduction. And so basically what CAPE and SIN is basically how much energy is actually like in the atmosphere. And so what you don't want to really kind of like use a surface, you can, but mostly you want to kind of use like this most unstable or the mixing layer. And so like what you kind of want to shoot for is at least like 3,000 joules per like kilogram or something like that is what the units are. And you'll see over here, this is like a hodograph. And so like what you want to kind of see is like kind of like a steering motion with the winds. So like this, that's not really great for anything. Like there's a whole bunch of different.
What
like
you mean by great is that if it is steering, you're looking at a
so
problem.
I think you're
Is that
using.
what you're
I think you're
saying?
using the wrong.
The wrong
I think you're
term of
using
great.
great.
So-
in a
Great for
different
you.
term.
so
Is that what you're saying though?
So the way that these things kind of work is like you're doing it from like you evaluate it from like different heights. So like this red line, I think is like from like 0 to 1 kilometer. I think the next one is like 0 to 3, and then like 0 to 6, and then like 0 to 8. And
Okay.
so you kind of want to have like this curving motion with the atmosphere with this hodograph to basically say like a strong storm. So like here where it says like possible hazard, you know, it says like none.
Mm-hmm.
You know, like sometimes it'll
So
say
really, we want that to say none.
yeah, you like
You wanted to say severe.
I wanted
probably.
to say, you know, like thunderstorms or
yeah,
tornadoes
So- okay.
and stuff like that.
Yeah, we wanted to say none.
Yeah. And so like, you kind of go through these and you can see how it like changes throughout the day. So you can see like here.
So
know,
you're saying with those green and red lines on the left side there that it should maybe be snowing there or raining or something, or there should be some kind of precipitation in the air
right.
because they're touching?
It not necessarily.
Okay,
It's just that you see all this
it's
moisture.
moist.
Yeah. And so
Okay.
you'll have clouds at least.
Okay.
And so yeah, you can kind of go through. And
Can you
just-
like go to like any day? Like, can you see any day?
Oh, it goes out like 300 and some
Can you
hours.
go back too?
Like past data?
Yeah, can you go to past data?
Oh, I don't.
That's okay. I was just wondering. You don't have to. I was just asking.
Yeah. So usually this. So like, and so like here we can get into like our observation kind of stuff. So like here, you know, we were saying like observe precipitation or like for us, like, you know, we want to look at like snowfall for like this season. So, you know, like in the last 24 hours, it hasn't like snowed at all. Last 48 hours, 72
It
hours.
snowed today.
Where?
Here.
Did it snow just at your office?
No, it snowed at the school. There was flakes coming down today.
It was south of Columbus or around Columbus. It was
Oh, there's like freezing rain. Yeah.
There was some. There I had some flakes on my
So you can kind of
Check it.
classify it as like a trace amount is what the scientific event is, like traces.
I'm just saying.
So then like let's say like how much like snowfall like have we had for like this year? And so like we can go down here and so like what is from
We haven't had like nothing.
so what is this 9:30? So what is that September 30th
September 30th.
to like today?
Less than 2 inches.
Norfolk. I wish they actually had this on.
Look at Manhattan, Kansas.
Yeah, so like
So-
that's basically that was that one day.
Yeah. My
Right.
question is, if we look at the rest of the like south below us, have you seen like a trend of snow moving more south? Snow systems?
It's
Because it seems like people south of us have been getting more snow the last, 5 years.
well, it kind of deals with like where the moisture is at that time. So like with that stuff, like we had that pool of like cold air come down at that time, and so like you just had the Gulf there mixing with that cold air, and so then at that point, instead of being like rain, you were just getting snow, and parts of Louisiana, Arkansas, those places don't see like a lot of snow. So like with those kind of places, they basically kind of say for us, what is it? A couple inches of snow, like we can handle. Those guys, they don't have like the equipment.
Oh,
to,
they
like,
can't even handle a dusting.
Yeah, I know, because like
I think
even
they cancel school for like 3 days down there.
I think even at like Atlanta, here like we have like those wind chills that are like really cold, and
Yeah.
they cancel school for like like 10 a.m. like that one day.
Yeah.
Whatever it was after Martin Luther King Day, where they canceled school
Yeah.
in Lincoln and Omaha. Those places canceled, but Norfolk is like a 10 a.m. start.
Correct.
Like, like overall, like if you look at the state of Nebraska, this is really kind of like depressing to see. Scottsbluff has only got less than an inch of snow.
No,
Shadron's got like 4
I
inches.
think you're wrong. I mean, in all honesty, the best time for a drought's right in the winter. Like, just it's perfect. I hate snow. Like,
Yeah, and my wife hates the snow because like she just gets anxiety like driving on snow because she's just even though
that
like,
doesn't bother me. I just hate snow. I hate cold. I'm a.
But that's
I'm a
what I was kind of
summer
getting
guy.
at, is that it just, to me, it just seems like, I'm not even talking like those stuff we had way down south. I'm just saying it seems like the systems have moved to Kansas, Oklahoma-ish.
it's all
Like they just
with like the
shifted
weather
south.
pattern. So like this one weather event, like this Manhattan one where it got like all of its moisture. So like there was
Yeah.
basically just that one low pressure system that went through there, and it brought in all that cold air, and you had all the moisture from like the Gulf, and you just had that one really heavy rain event.
It's been pretty dry around here, right? As far as
Right.
like
so
no moisture in the air.
even like if
So I
you
can
were,
feel that just in the house. Like it's not.
so we actually have like the University of Nebraska has like the drought monitor, and so like if we were typing like drought monitor or stuff like that for like UNL, let's see, is this the one from the?
It says UNL.edu.
Yeah, so this is like my friend, she makes these kind of like maps, and so you basically see like the state of Nebraska here, like the entire state is basically in some sort of like drought. So like Norfolk is considered severe drought. Lincoln is moderate, but that's this basically kind of goes back all the past year. So like let's say March or April or whatever it was last year, we didn't have like the state in in drought. Nebraska basically got all of its rain last year in like March or in April,
Yeah.
and then like after that, so you had all that rain during the growing season, but then you didn't
Yeah.
have any rain during when you actually need it. So like now we have like no snow, and so this is why it's kind of like bad for farmers. Farmers, they want the snow because they want that moisture.
Yeah.
And so you kind of want then that runoff from like all those other places to kind of get down back into the aquifer. And so, with this drought, and it's just only going to kind of get worse, I think, this year. It's going to probably get much worse. I don't think it's going to,
You don't see much for precipitation coming?
I don't see it really getting better.
Gotcha.
I think it's going to just more or less intensify as the year goes on.
Gotcha.
But yeah, so like Lincoln and Omaha, they got like so far just like only 2 inches of snow. But I think like their airport, I think it was like doing like 1 inch because I think they always put like all these different like news events saying like, oh, Eppley only has like 0.9 inches, which is like the lowest, and you know, it goes back to on record, and you can kind of go through for like anywhere. So like if we were to go to like New York, you know, you see here, you know, can like anyone guess like, you know, why like Jamestown, why Syracuse, or why Watertown?
Off the lakes.
Lake.
Yeah, so you get like your lake effect snow.
Snow.
Yeah. So like here, let's go to like Wyoming. Like how about this one? Like why is there like this pool of like dead here, but then like you have this
mountains?
Yeah. So like this would be like the Bighorn Mountains that are here. So like you have no moisture here. The clouds are going up, you know, the mountains, and it's just getting all the snow down, and it kind of goes on over to like Sheridan. And so like that's kind of like home to me because, you know, my father's from like Sheridan, so I kind of like keep tabs on like the Wyoming weather. And so it's always kind of like disheartening, you know, like when you go out there and there's like fires that go through like the area. But yeah, it's always nice to kind of go through here and look at all these different like models, because like not one single model here basically like will give you like the answer that you want. So like there's these different global models, and so like, you know, I was just doing like a precipitation. So get off. Nope. Go back to like, and you don't have to just look at like here's like the weather. So like here, you know, Sheridan's like -9. And you can kind of see like what is it going to be kind of like, you know, for like the coming days. And so like when you first asked me to kind of do this podcast, you know, a couple of weeks ago, and when the first like available it came out, and so like I looked at like 6 o'clock during this time, and it's had like a wind chill of like -30 degrees, and it's like, you know, you're looking at like 300 some hours, and obviously it's not going to be that. What we like to kind of, it gives us like an idea of what the weather is going to be.
How accurate usually is it?
So within like a couple of days, we should say that, you know, it's pretty accurate. If you go out to like 5 to 7 days, you know, it gets less accurate, and then after 7 days, it's really difficult to
shot in the dark.
Yeah, it's kind of like up in the air at that point, because it's the models running for that long kind of get less and less accurate over time.
Okay.
And so, yeah, and that's actually one of the things that I'm working on now with TCQ is we're doing these simulations, and they are wanting to do like those WRF simulations again, but they want us to do a 1 month continuous run. And so like what some of these we'll do, like when we do our data sets, you know, we'll run it for like 30 hours and do it and reset it. With these, when you do it for like a 1 month continuous run, like the models just kind of go amok, really, because there's nothing there to kind of keep it in track. Mm-hmm. And so what we are tasked with doing now is putting in observational weather data. So I'll take data from like their sites that they have and put it back into the model, so that way it doesn't run amok. And it's basically just kind of verifying and saying, you know, which for like TCQ, like what model is going to be best for them when they do like their NACS concentrations, or which ones are better for like monitoring like ozone or PM 2.5, which conditions or which parameters are going to be best to give us a better predictor than.
So where's the data coming from for Pivotal then?
This is just like all different. So what happens is at the National Weather Service and all these different places around the world, they launch these radiosondes at the same time every single day, and it's at like 0 UTC and 12 like UTC. So everyone goes out there with these like weather balloons, and it's just like this little tiny box, and it goes up in the air, and it gets data. And so then the data then gets fed into like these supercomputers at like NASA or wherever, like Storm Protection Center, and it just kind of creates these models. And so like the ECMWF, that's the Met Office, the GFS, that's an American one, and like another one is like the regional one, the NAM. This is like the American model that we'll use. But like, let's say it's like severe weather time. So like we have these, they're called CAM. So it's a convection allowing model. And so like this is what I'll use for like the summertime. It's like what we kind of like to use is kind of like the HER, or like this FE3 is kind of like what I like to use. And so if I go up here and go through like the central US. So here we still go through, we see that this is now per hour. So like this is like what, like whenever you like text me and say like, what were you doing? Were you doing the Relay for Life kind of thing? Was that what it was?
That was what Anita was doing, and she was texting me, asking me if she should get out of there. And I said, well, let me text my friend.
Yeah. And so you can kind of see
We
here.
were in the bathroom. Because you said go to the bathroom.
Yeah.
You said go to the basement. And that's the first time you've ever said that. I think you actually texted me that time before I even texted you. You said you should probably go to the basement.
Yeah, because I think that's the one that where it hit the building on the outside of town.
Yeah, I think so.
And so these ones are higher resolution. So like these ones are out every 60 hours. And so you can kind of see where that low level system is. And I think even now, like there's going to be like a train of like low level systems that are actually going to come through. And theoretically, if the models hold up, we could see anywhere around like 9 inches of snow. If that actually holds up, I highly
Here?
doubt. Yeah.
I
But
figured we weren't done yet. There you go, buddy.
Punxsutawney Phil saw.
Because we're gonna
6
believe-
more
we're gonna
weeks
yeah,
away.
believe
we
the
still got 6 more
groundhog.
weeks.
We always have 6 more weeks of winter. It doesn't matter what happens. The old Punxsutawney.
That's interesting stuff, though. What's a subscription to that?
What's this? So like this, you can do like a free trial for like 7 days.
Yeah.
You can pay like $10 a month, or you can do it for like an entire year. But like, let's say that I just like sign out of this account, and so like here is just like like the main homepage. So like you can still do like the same. Yeah, I know I have an account.
Hobbyist.
Yeah.
Love that.
Well, because there's 2 different kinds. So if I were to basically use this for like, if I were to basically try to make money on like Facebook or something like that, they would make me try to do like a commercial one where it's like an extra like $100 like a month.
Okay.
But I don't want to chase out storms. I don't have the money for chasing storms. So like this is
You don't want to be our weather guy?
unless you guys want to fund like a third vehicle.
No, you can just
like,
sit here with this and say, hey, here's what's going on.
So yeah, so like here you kind of just lose like the in-state views, but you can still get like Nebraska and all this stuff. So you still get like all these models that you can still kind of look at. You still get like the FE3.
Oh, so you can still kind of see it.
You can still see everything.
In.
Yeah,
you
it's
just
just
gotta know
like-
where you're at.
Yeah, so like Norfolk is like right here.
Okay.
So like if you pull up like the SQT for like Norfolk, Nebraska, so you can see that it's relatively dry. At the surface, you get some sort of like maybe some low level clouds here, some high level clouds, and then again you have no clouds up in there. But so like it has all these different parameters. So like you can see like a wind, the temperature, and so like what's nice here is like they got these severe weather.
Colorado was wild.
Well, that's because of the mountain ranges.
Well, I know, just wild. Looks like Declan drew on there.
And so like, you're looking for like hail. Let's say you're looking for a hail. So like here you have like updraft helicity. So I know probably more than likely it's not going to have any updraft helicities at this point since we're in like winter. But like you can see down here. I think what I say is no. Somewhere between 50 and 65. I think are like thresholds. Also like here you can see that something's kind of like registered for like an updraft helicity. So like there should be maybe some sort of like thunderstorm that's popping up here in like Missouri. But like here you can also see they have this like significant tornado parameter. So like this is kind of like what the Weather Channel kind of uses. And so like you have like Torcon 8 and 9 and stuff like that. And so like here Missouri, Arkansas is like 0.5 or something like that. So if you wanted to like kind of like focus on like chasing or like where areas of like significant weather are going to be, you kind of want to like target it like those kind of areas.
So you can still see that without a paid subscription.
Correct. So and that's like the beauty of this. Like everyone, I think everyone can relate to the weather. You can talk to the weather, but like nobody can really like understand it. So like you just always go to like the National Weather Service or the Weather Channel when anyone can go out to like this website and they can look at the weather themselves.
Right.
And so that's kind of like just bringing kind of like the awareness and saying that, because I was trying to teach this to the car salesman, because he's texting me. He's like, hey, is it going to be hail? Do I need to bring in all these vehicles? And you look up the updraftilities and you say, yeah, the conditions are right, potentially for hail, and so that way you don't lose money on the vehicles,
Right.
park them inside and stuff like that. And so there's just these fun different parameters I can do. So like here you can just still, there's the winter weather, and so like here you can do, what is typically what you would normally do is it's a 10-to-1 ratio. So 10 inches of snow is like 1 inch of is liquid water is what you would do. Or there's like the Kachira ratio, and you can kind of see like what is the snowfall for like what is the like next 60 hours going to be. And so in this model, so it says here in the next 60 hours, there's going to be like no snow for like Norfolk, Nebraska.
There you go, 60 hours, Vance. No snow.
But then if you were to kind of go for, let's say, like the GFS, which I despise, you can kind of see like, oh, look at that. In the next like 300 hours, it's what? Roughly around like 3-4 inches of snow, or let's say the ECMWF. Oh, they don't have the Kachira. They only have snowfall for this one. So you go through that. Like, oh, look, there's 5 inches of snow, 6 inches of snow. So you see, like, you kind of have like maybe an idea of like how these weather systems kind of affect and see what it's going to be. So like this might be, maybe our first thing. So even then, so you can see it play out by hour and hour. It's all kind of like neat stuff to kind of play around with.
It is. It's a cool website. I'll have to remember that.
And so like you can also go through here. So like the National Weather Service will put out like the maps that I'll sometimes show. And so like here I'll say, like 24-hour ice. And so like here in eastern Iowa, it's got, 5/100 of an inch of ice over the next. And so I can see like snowfall for like the next 6 hours, 24 hours, and 48 hours, what the National Weather Service is thinking that, it's going to snow. Another thing is, so let's see. These are like outlooks. These are also kind of useful for like storms. This basically comes from the Storm Prediction Center. Obviously, you're not going to have anything during the wintertime really, but like during like days of like severe weather, you might see, orange, red, and purple, for like hail or tornadoes and stuff like that.
Yep.
And so, those are kind of the areas that you want to kind of be. And so we have all these different days. So like day 1, 2, 3, 4, 5. And usually once we get out to like days like 3 through like 7, it's usually so low. But then there are times where they are pretty confident where they say is like, hey, 7 days out, we are tracking the system where it could be, really potential. So like we can know really like kind of like a week ahead of time, like, where severe weather
Shit's about to hit the fan.
Yeah. So I kind of get like prepared and ready. So like even over the course of like 24 hours, these weather systems, they can change drastically. They can move hundreds of miles in the north or south directions, or move slower than what's supposed to be. And so it's all fun kind of stuff to kind of work with. And it was fun for me to kind of work with that one day where, I told on my equinox.
Yeah. Yeah, definitely.
Yeah, where the tornado came through, the hail came through that the National Weather Service that one day.
Right. Interesting. That's really cool, though. Thanks for showing us that.
Yeah, because otherwise here they have like the tornado. So there's nothing here for like tornado. So like they break it down by, nothing, marginal, light, medium. So like anything that you basically kind of get into like the 30% and more, that's kind of like areas that kind of want to avoid or watch. Hail. They're kind of calling for like a 2% chance or 5% chance of hail in southeast Missouri. Wind. Where's there going to be wind? So like for me, since like my place set, kind of tipped over that one day.
Right.
It was been smart of me to take down the tarps that way.
You knew it was coming.
Yeah, I did.
Yeah.
I had to live that one down with the wife. It's like, yeah, you kind of knew that this wind was going to be kind of windy.
Right.
But it's always kind of weird because, up there, just like a block away, it's just like an open field.
Mhm.
So, but then let's say like your neighbor that's just like right down the street, he's got like the same place that he's still got his tarp up on his
Right. All
thing.
depending on how it comes through, right?
And so, yeah, it's also like the surrounding topography. So like there's other houses that
Yep.
are kind of blocking, and then there was nothing in like my area. So like, it's just like a straight line wind that just kind of like blew it over.
That's wild. Do you want to get into the EV stuff? Or you still got more on here?
No, not unless there's like satellite stuff. Otherwise, like forecast, you can kind of see, like the next like 6 days where they say, it's going to be, below average temperatures. 8 to 14 days out, it's going to be cool. Precip. They're saying, over the next 6-10 days, it's going to be above average. 8 to 14 days. Equal chances. But yeah, it's just a lot of stuff for you to kind of like play around with. And you can see like all the different like weather hazards that are like currently in effect.
Yeah, that looks really cool. Like that. Thanks for showing us that.
So like another one of the, let's see, which one do I want to talk about? Because we'll save. Oh, we can talk about this Texas thing. Because then I can talk about, or maybe I should talk about this for storms because that's more like weather. We're still talking about weather. So here we're going comparisons of satellite detected hail climatologies in subtropical South America and CONUS. Oh yay!
Does it work?
Yeah,
Okay.
I can use the clicker. So like the motivation. So like you can see here, we have this area of like South America here. So like this is hail occurrences. So for like satellite detection in the U.S., you can kind of detect as well. So like, the United States, we have like those radar systems that we have tracking, but like South America, you can't like really track it. So you have satellite. And so, this is like a hail prone region. So like these are potentially large and organized multicellular systems. They peak late at night, early morning. And so we use these satellite-based hail detections for both subtropical South America and CONUS. And we'll see if there's any differences in climatological and see if there's any differences in like, South America hail or CONUS hail.
Mm-hmm.
And so then we can, identify these then with that as, like another WRF simulation, but this time we're going to be doing the WRF LES. So the LES basically stands for Large Eddy System. So it basically kind of handles.
Does it hail over the ocean?
Yeah, technically, yes.
Okay, I just want to make sure.
But because I think my next slide, yeah. So yeah, this is the data that we have. So we classify these in 3 different ways. So like a null data set, a medium. So when we say null, medium, high, it depends on the hail probability that the satellite has.
Mm-hmm.
So anything that's like less than like 22%, they classify as null. If it's like 25 to like 47 or something like that, would it like be a medium? And I think greater than like 54% or something like that, I think was like a high. I can't.
Okay.
And so like this is a program that I wrote. So on the left side that we have, this is actual satellite data. So this is the GO16 full disk data. And so what I do is I develop this program that basically kind of tracks this storm, but I'm only caring about brightness temperatures that are like 210 degrees Kelvin or less. So basically at 210 Kelvin, you're basically kind of getting those brightness temperatures that you would see with like hail. And so what this black star here is like, this is when the satellite first detected it. And so you're kind of seeing how the storm moves and forward in time. And so the reason why we track it is because we want to know where it initially started. So we go back, let this thing die. So it started like around like 11 UTC, and we identify it. Let's say there, so about 0 UTC.
Okay.
So that what? When I say 11 to 0, so that was like 13 hours that tracking it from like when it first started to the initial time, and then it, then it dies here like another so this is like a system that lasted for over like 24 systems. And
Wow.
so, these things you're looking for deep and wide convection. And so you're getting that deep part and you're getting that wide part. But, the only thing is like, we're not kind of like verifying this, that it actually, I think, hailed at this point.
Gotcha.
And so here we can kind of look at like the environmental parameters. So on this side here, we have this pre-CI. So this is like convective initiation is what we call it. And so like that would be like that very first point where we first detected that storm. So I get that 11 UTC. And so we count all these up. And so this is like how much moisture is in the atmosphere. So within like the 1 to 3 kilometer, you can see, in the Knolls, it's higher for like South America, and the highs it's lower. But compared to like CONUS, it's kind of like relatively like the same. Deeper levels, it's kind of like the same, but you can see then the differences between the high cases and the null cases. And here we're looking at the shear, and this is basically kind of identifying, what is different, like shear patterns between subtropical South America and CONUS. And you can kind of see it here between the United States, that you can see a difference in, the highs and the nulls. And this is what you really want to kind of see, that there's different parameters that there is different like thresholds or parameters that you can identify. So if it has like this, so if it's got low shear or high shear.
Okay.
This is like the V wind, and you don't really see too much difference, but like the main thing that you can kind of take away from this is where these like low level jet is. So like with the South America, the low level jet is lower compared to like CONUS. Then we get these mixed layer capes, most unstable layer capes, and the mixing layers. And so here you can see how these storms differentiate between the United States and South America, and you have more energy within the ones that are in the United States compared to the one in like South America. And so like I'm really only talking about like these two over here.
Yep.
The ones that are over here, these are like pre-hail CONUS. So it's basically data didn't exist for like GOES during that time. So you would be basically pulling 18Z from the day earlier.
Gotcha.
And so you don't really, it's not that you don't really care too much about it, but you want to really compare like these two. These are two that you can really kind of compare. And so these are like the lapse rate. And so, these are also kind of interesting where you see such a huge lapse rate, like 6 to 7, degrees Celsius per kilometer. So you want to see these highs, a huge difference between the highs and the nulls, basically saying that you are detecting like hail or not.
Okay.
And so then what you kind of get into is like, how big are these kind of like systems? And so that's kind of what we kind of do here. And so like when we say the 30 dBz area, when you look at like a weather radar, you have like, it gives you a dBz value. And so what I'm doing here is getting a 30 dBz and connecting all the dots that are like all together and how big they are. So this is 1 point e to the 5th kilometer squared. So like these are like I said, big storms, the outliers. And so between the United States and South America, they're roughly the same. But when you have the 50 dBz, you can see that the United States ones are much bigger than the South America ones.
Interesting.
So now you kind of want to get into like the kernel density for like the high and null cases. So the solid lines here are high and the black lines are the null cases. And so like you'll see a shift in the pattern, like when do these storms like occur? So like in the high cases, you'll see that for like South America, they tend to occur like around like 18 Z for their time, for local time, compared to like a null case, which is shifted more mainland and occurring at 15, but Iconis, it's closer to the Rockies at 21. In the null cases are shifting more off to the right in like Kansas area. And so here's like our ground-based climatological averages. And so like based on like different times, so like red is like the storm reports and the yellows is like the mesh reports, and you can kind of see that the storms are supposed to mostly be between like 18 mountain time and 19 local time. And so you got oh no, I want to go backwards. Back. And so like here we were saying, like the null cases, you were saying that we're finding, it'd be, 15, 18 time, but like with the satellite data, you're saying it's 21. And so that's what I'm trying to get at here is like, you're kind of missing them with the satellite compared to what we have for like ground base. And so here we kind of get into the WRF simulation. So once again, this is like one of those, this is real time data for like the GOES, and this is our WRF data. So we take that ARA 5 and we basically take that data and we throw it in there. And basically what we're kind of looking for is like, is it like the same shape? Is it doing the same stuff as like the GOES? So like in this case, we could say, yeah, it's doing what it's supposed to be doing. And so here we're looking at the most unstable cape. And so you kind of see here, like there's this red star and this yellow star here. You can see before it had like all this energy. And you see here, here's a storm coming through, and it's, there's no more energy in the system. And so with the WRF LES system, so this is like a simulated radar of what the storm would kind of look like for that system.
Okay.
And so you want, 30 dBz, 50 dBz, and so you can kind of see how it propagates. So like I said, like this is like the point where it identified like that at that point for that one system. And this orange star is like a rough as our point that we were kind of trying to like verify like an environment that's still close by to the system. And so what we're kind of talking about here with like these 30 dBz objects versus the reflectivity. So you can see that our shape is roughly the same as what we are simulating within the radar. So this is at the satellite time at 2244 UTC compared to WRF, at 23 UTC, it's roughly about the same.
Okay.
So that's all nice and dandy. So like I showed you those SKU-Ts before for like the weather systems. And so like this is like, like a real-time application. So this is, what WRF was like simulating, and this is what that environment was simulating at that point where we first observed it. So we were trying to find like some sort of point that's kind of looks like the same, not exactly the same, where you see some sort of like, drying here. It's not as like sharp. Mm-hmm. And so what we'll do is then we'll take this sounding here and then we'll put it into this cloud model. And so we can see, this cloud model evolve in time. And at the moment, this is like what we're doing. So everything that I've shown, we're actually it's going to be putting into like a paper, and here in the next couple of months, it'll be, submitted and hopefully accepted. But this is the point that we're at right now, is trying to match like this cloud model simulation, because what you can see here is, it's becoming more spherical instead of more linear. So like when you were watching the WRF before, it's just like a straight line kind of coming through. And here you can kind of see how it just kind of like bow echoes. So that's kind of what we're doing at that point. So once we have that done and simulated, what you can do then is you can take these hail embryos and then you put it back into the cloud and have, I can't remember, it was like 1 million hail embryos, and you can see how it kind of just moves up and down within that column of air.
Gotcha.
And so basically you're kind of trying to verify that given all these different parameters that we were doing, that at that one single point that we can basically say that it did hail at that point.
Wow. It's interesting. exit out of that.
All right, so we got another one. So now we can kind of get into like more of like the aerosol kind of like background that I've like done.
Yeah, let's get into. I want to get into the EV stuff.
Oh, you want to do it now?
Yep.
Okay.
We're kind of running low on time.
Oh, okay. I don't know if we can do like a 4 or 5 hour.
No, no.
Oh, you guys got bedtimes.
We'll lose people's attention. Well, no, we'll lose people's attention by then.
Oh, all right. So yeah, we'll go to the battery fires here. So this is kind of like
I'm gonna put this up. I'm gonna go pee real fast, but you can keep going.
Okay.
Okay.
All right. So we talk about these battery fires. So like I said before, so what we use is we use this ski chem model. It's version 3.3. It's a second order closure integrated puff model with chemistry. Anyone can go to this website, this GitHub, and download this data and use it itself. It's a reactive non-steady state plume. It's single sources and multi-source impacts. And so basically, you're basically just trying to see, given you put like a pollutant in the air, how does it react with the atmosphere and how far does it kind of go? Is basically kind of what we're kind of simulating here. And so like what the process are, you set everything up. You can put in like a background emissions if you have them. Otherwise, you kind of just have to kind of put in like the meteorology and the terrain of the area. And then you put it into the ski chem, you run it, and then you run post-processor on it. And so all the things that kind of go into this, and so like, like this is like a windrose for a surface station for like Atlanta. And so normally like when we get these things, we're supposed to do like a 5-year simulation. And so we basically kind of say is like, you don't need to run like a 5-year simulation. So what we can say is like, if we were to basically run like 2019, we can basically say that's basically the 5-year would be good enough if we just ran this one single year. So we're saving them on costs and us on costs, and basically say that they should be relatively similar. But, the thing is with this surface data is that, we have to put in a minimum wind threshold of 1.5 meters per second. So that's roughly like 3 miles per hour for like a wind. Because when you do these model simulations, the equations that they use, and they use wind, like wind is in like the denominator. And so if you basically try to divide by 0, these models will just kind of go amok, and it takes forever for them to kind of simulate that. And so that's why we kind of had to align it to like the past weather data. So like if it was at like 0 UTC, if it was like calm wind, we would try to find like the next usable, like good surface time. So that way that you would actually have something that's actually kind of like usable.
Like how often on the weather side is it actually 0?
As actually like calm wind?
Like 0, 0. Is it? There's always seems like there's something moving, isn't there?
It moves like relatively slow, but the atmosphere is continuously moving. But there's times where we have areas of like high pressure or clear sunny skies. Those hot days that just
feels like it's not moving. But
it doesn't move. Everything is just stagnating, and so you get those, and that's considered like calm winds. So it's not moving enough. And so like in those like type of situations, that's where like the model will like not really overestimate. It's just stating like it just kind of like runs amok. So it just runs away worse than what it should technically do. So we kind of put like a damper on that. And so like what we try to do is, a battery has like 2 phases. So we calculate, emissions. So this is called like the runaway stage. And so most of the time, like these battery capacity sizes will be given to us, and we kind of like assume like a bulk energy density of like 125 watts per kilogram. Anywhere between 100 and 200 is the typical range. We assume gases are released with negligible buoyancy, and that basically means it's the same temperature outside as what it is inside. Vertical velocity is like 1 meter per second, so it's coming out of the vent very slowly. And the port height is at like about 2.5 meters. And so we'll say that there's 2 modules are in runaway at one given time, and it takes 2 hours to release all that gas. So we assume the release rate, and we get this 28.25 moles per watts, and we assume low state of charge, and we get this grams per molecule and high density. So that gas is going to be staying closer to the surface, and that's what we don't want is this runaway stuff, because then you have all these chemicals that you just breathe in, they stay at the surface, and you want like a well mixed atmosphere, so that way it's not as bad. So like how these, like here's like an example. This isn't something that's actually been modeled. So like let's say we given this battery capacity size of like 100 kilowatts.
Yep.
And we put in their grams. So like there's 2 modules and it's 7,200 seconds. So like that total emission that is being emitted is like 30.13 grams per second.
Okay.
So then we assume HF, this hydrogen fluoride, is in thermal runaway, and we have like emission factor of 0.4 grams per kilogram. So then we take this emission factor, times it by the battery's weight, and again, how long it burns. So of this total emission that is being burned, we're saying 0.89 grams of hydrogen fluoride is what's being released out of this total gas, or roughly about 0.3 of that total gas is HF.
Okay.
And so what we will then do is we will model this 30.13, but then we will scale it with this 0.3 factor on it. That way it gets to that HF. And so like what runaway is this battery. So like this battery has been abused, and now it's emitting all these toxins, and now it's caught on fire. And so this is what we don't want. So if one module fails, it's going to catch on fire. The next one below it or above it's going to catch on fire. And so like it's really critical that you kind of get these things under wraps really quick. And so then, like I said, here's the second stage, is the combustion phase. We assume that like a release height of like 10 meters. So like that's like 30 feet above the air. So like the smoke plume, that's basically where we're kind of emitting, is the smoke plume that we have. And once again, we say 2 modules, they burn completely in an hour. This heat release that we have is 1.1 megajoules per kilogram. This can be 5.3 megajoules per kilogram. We assume that emission rate of HF is 20.81. In this case, then we say that the entire thing is 1.156 grams of HF per second. And how much energy is available is like the 0.488 megawatts. And so now we got to calculate this buoyancy flux. So all these complex equations, so these are just constants that we have. So like this density, put in your energy that we have. So this flux is, 13.24 meters to the fourth, seconds to the negative third. So then at 10 meters, it's moving at 2.3 meters per second. And then you got to model what is the exit temperature, and we can calculate that to basically be, 22 degrees Kelvin, or, we take that 25 plus that 21.99, and then we get our 46.99 degrees Celsius. So at 10 meters, that's what we are basically saying, how fast it's moving and how hot it is. And so then we have these thresholds. So we have 2 different kind of thresholds that we kind of use. This is the acute exposure guidelines levels. We model it as the 1. And at stage 1, it's notable discomfort, irritation, certain asymptomatic non-sensory effects. However, the effects are not disabling or transient and reversible upon cessation of exposure. And then there's the other one where it's immediately dangerous to life or health. So like if you get into like this area, then it's kind of bad. So here's one of the simulations that I kind of did. So this is the company was kind of concerned that here we're going to put this battery container right here next to like this like country club, I think it was.
So the star
is where like the battery's at.
Okay.
And so what I did in this case is I modified the winds to be purely to the east and moving at like 2 meters per second.
Mm-hmm.
And so if like on a given day, if it was, a west wind moving at like 5 miles an hour, what would like the concentration be for, the people that are playing tennis at this place? And, before I had this being as parts per billion, so I didn't factor that in. So anything like 800 micrograms per meter cubed, that's basically where we're going to say is bad.
The
So
red.
like,
okay.
and so like in this case, we're measuring rural versus urban. And so where you place these containers is also like a huge factor. So if you put this in like the middle of like the field out like on like a farmland, it's going to be a lot less dangerous compared to like if you put this in the middle of like a town.
Okay.
So like even though like here, we say it's in town, you still have like more concentration. It's still, not that bad. But this is just like a single battery case. So where am I at? All right. So here, let's say like now we kind of modify. This is like a rack scenario. So like in this case, there was like 17 batteries within like a single rack. And so once again, here on the left side, we have like the rural setting, and on the right side, you have like the urban setting. So anything in like the orange right here, this is, what you're getting into as being like, discomfort for people, and these are, I believe, at the 1 meter. So like this is like children kind of like stages. So like there's not a huge difference between like 1 meter and 2 meters.
So that's not like immediate death. That's just
No,
discomfort.
It's discomfort. So they basically say like, if me just kind of want to go explore, it's like, oh, hey, this container is on fire or something like that.
Yeah.
And I stand there for like an hour. I don't have like a breathing apparatus such as like a firefighter or
Yep.
stuff like that. And I'm just sitting there, just breathing in this fire, these chemicals for like over an hour. This is where it's saying, like if you're within like this certain area, this is where it starts to get bad.
Okay.
And so then we kind of then can also simulate then, like what happens if that entire container, were to, catch on, in thermal runaway. And so here, you can see, in the rural setting, it still doesn't matter. It's still, starting to kind of get bad.
Yep.
But in the urban, you can see how much of a detriment it is to like the people that would be playing tennis in this case.
What's the difference between the urban and the rural? It's just that there's more wind
It's
on the rural.
No. So these are both. Wind is locked at like 270 degrees. So the wind is blowing to the east at 2 meters per second.
So I'm confused by just looking at the two pictures. Why one's rural and one's urban?
So it's different land types. And so what I'm trying to get across is like where you would put these things. So given this same kind of parameter, so like if I put this container.
Yeah, so what he was saying is that it's an open area, so the wind's going to blow and it's going to keep going. Whereas in the urban area, it's going to hit buildings.
No, it's different parameters that they put in. So like albedo, like a planetary boundary layer, just a different kind of mixing that's allowed to kind of go through. It's different. It's like all the different background concentrations, different values that kind of go into it.
Gotcha.
So there's different values between like a rural setting and urban setting. So like you would have more concrete in the urban setting. So you're having more heat being available in that area.
Whereas you'd be on dirt or whatever, it could soak some of that stuff up. And that kind of makes sense a little.
So like where you
because it was confusing me on the picture. I was just not understanding. You know what I'm saying a little bit.
Yeah, and that's kind of like where we kind of tell these companies like, hey, it really kind of matters, where you put these things. If you do it on the outside town, so like I think the next one, yeah. So like this one, like how far will these things travel? And so like we usually do like a 2 different simulations. So like this one is a 1 kilometer simulation, and this one is like a 5 kilometer simulation. And in this one, you kind of get more points. You can see that it's over 3,000. So like in this case, this is where it would be like that immediate danger to the life.
Okay.
And so because I think there's like a town that's supposed to be like right over here. I kind of blocked out these towns so that way, like they can't see. It's like, oh, where's this exactly at? But so like here's like kind of like a lower resolution. So it's able to disperse further. And so basically everything that's within here is, on the lower end, but then everything in here, this 3,000, that's immediate. And so it still travels, still pretty far, roughly like 1.5 kilometers these things can travel. And in this setting, it was like a forest setting. It's because there's a whole bunch of like trees around in the area.
So it's dangerous.
It's still dangerous. Like I think this one was one of the more heavier batteries that we kind of simulated. The one that we just got done doing, it wasn't too bad.
And so when you talk about battery, this is just one single vehicle, or this is like when you had like 17 batteries and 51 batteries. Is that what is in one vehicle, or what is
this is a vehicle. This is like a storage container kind of a thing. So like, yeah, when I say like storage container, so like let's say
Like a charging station?
not
No.
a charging station. No. So this would be like, so when I say like storage container, so like a 53-foot trailer. It's
Okay.
not, but it's like maybe like a third of that. So like, let's say it's like 10 feet by like 6 feet wide or something like that is what these like containers are. And it's just full of like racks of like batteries.
Just to put in vehicles then, or
No. It stores the energy.
oh,
And so
so this isn't for EV. This is more just the battery. Just
this
storage
is like
of-
battery storage, like
For,
where
like,
the
your-
housing is.
Okay, so like from solar panels or windmills or
It's just where it gets stored. Like all the energy gets like put into like these batteries to
Yeah.
be used
okay.
somewhere else.
Okay.
But that's what I'm saying. Like it's a storage container.
I get it now. Yep.
So yeah, that's why it's like if one of these containers were to just kind of
Blow
like
up.
blow up, and so but you do kind of see like a container that's over by Hy-Vee, where you have those charging stations that there's like that one or two boxes or whatever. It's kind of like that, but it's like these kind of simulations are like on like
A
a larger scale.
Yeah.
So like something like that would be over.
So like
kinda
the solar farm outside of town too would have to store them somewhere, right? That doesn't just go somewhere.
Yeah, it has to be like stored somewhere. I don't know where.
It has to be
It's-
somewhere right around. I guess I've never looked to see if there is a storage facility out there because it has to store it somewhere. It doesn't just keep running, right?
Yeah.
Yeah. Okay.
And so like here we'll get into like this EVs and Powerwall simulations. So the one that we modeled, we assumed like a battery size of like 40 kilowatts and a density of like 229, a weight of like 175.
Okay.
So like cars today, they're easily twice this battery size. So I think like even like the newer models anywhere between like 80 to like 120. So then we kind of assume like a high emission factor due to the rest of the car. And so like we'll say it's like 63.8, and this hydrogen chloride, that's 404. And so like this other one is the Powerwall. So you can see here that it's relatively small. So it's like 13.5.
What's a Powerwall? That's a charging station.
No, like the Powerwall is like if you have solar panels on your roof,
Gotcha.
and you want to store that energy, you would connect it
That
to
way you
that
have
Powerwall.
some at night.
That way you don't have to use like less electricity, or you can sell it back to like a power company and stuff like that.
Gotcha.
And so like we assume these to be like on the side of a house, and it's next to another house. And so here's the electric vehicle simulation. And so basically anything that's purple here is basically, the AGL simulation, and anything that's in yellow would be really bad. And so like I said, like, this is like a car from like 8 some years ago, and
So you could double it.
yeah, you can basically double it to kind of like triple it. So anything that's basically kind of like here and like the green, more than likely would probably be at this point somewhere between like the yellow or maybe on the low end, the orange. And so like another thing that they make us do is these MET studies. And so basically saying for 24 hours a day, 365 days, like what is the distance that this threshold goes. And so you can kind of see like how far like this lowest one of like 1,000 will travel. So like here, like here's 269 meters at like calm winds, 304 meters at calm winds.
Mm-hmm.
And so you'll see these higher concentrations during like the nighttime compared to like the daytime. And so you have more mixing that's available to go through during the nighttime compared to like the daytime. And so you can see how much like the wind helps down here. And so here's the other one. So like this first one, this is, like I said, the stage, this one's runaway, and then this one goes on fire. So like in a car case, the fire is actually worse because you're getting into the immediate danger to life. So like these these rings are basically simulating 100 meters, I think 250 meters, 400 meters, I think 750, and I think this one's a kilometer.
Do you know? So you mean say danger to life? How fast that
Ooh.
can happen
No, I don't.
with exposure?
I don't know what is classified or what is like what happens with those.
Because like on the right side over here, you're saying it would probably be in the red then. If we're
No. So it's not the red. So
okay.
what you were wanting to look at. So like
No, he's saying with a new vehicle with the
with
triple
the new vehicle, yeah,
It'd be in the red. Then.
yeah.
right
Yeah,
there.
so it'd be at least
at
twice. So it
point,
could be an orange or at least into like the red. So 30,000 is the threshold. So like even with this old vehicle, we're already seeing that it's already very extreme danger. Now, if you basically increase the battery size, then you basically say is like, you can basically kind of say it's anywhere between maybe 2 to 3 times as like worse.
Yeah. So, in the way that's traveling, you almost wouldn't be able to get away, right? Or I guess as you want to be kind of like outside of like this 1 kilometer kind of area, is what we kind of say. So like in this simulation, anything within like this 100 meter, is not the greatest. But let's say that you're timesing it by 3. Is that highly likely of death then?
I wouldn't say it's like highly likely of death. It's just you're exposed to that, so like you might have like some sort of like breathing problems, but it's more or less not for like me and you kind of like a per se. It's more or less for, let's say, like firefighters, but like the firefighters are going to go in there and they're going to have like the breathing apparatus. So this is like if like some dumb random person just like wanted to stand next and watch this car catch on
could
fire.
Be somebody that's in the accident.
At that point, yeah, the vehicle's on fire
or what if one caught out fire outside the house?
So in this setting, this is actually forest setting. And so once again, this is where, those land types come into place. And so again, it's in an urban setting. So like maybe like Norfolk or Omaha, Lincoln, then you're also having to increase this maybe by a little bit more.
That's what I mean. So like, let's say one started on fire on the street right outside the house.
Yeah. So then like the neighbors, like the chemicals in there that they're breathing in isn't like the greatest. So like
would that be an evacuation type thing?
Probably be kind of like an evacuation kind of thing. Where
how far?
Usually they just kind of, we don't recommend like an actual like threshold. It's kind of like here's the information, you guys kind of like do it. It's not us saying what to actually kind of like do. We just give you the information. Right. So like in this case,
you don't necessarily know the health hazards. You just know don't be by it.
Yeah, don't be by it. So like so like in this case, what we basically say is like for like this electric vehicle, don't be within that 100 meters. But in reality, with like a newer vehicle, you could probably say don't be within like a 400 meter radius of this vehicle, or kind of like evacuate in that area to basically kind of get out of that zone. But even then, like you have this little blob here for like 1,000. So even then, basically kind of say, anywhere between like a 1 kilometer kind of radius would probably be, safe to kind of do, because, we're only modeling, 1,000. I'm not modeling what actually, because there's other points that are going to be out here. It's just going to be less than 1,000.
Right. Also on that, is that all while the fire is still going? So like, let's say once the fire's out.
This is the maximum over the course of the year.
Okay.
So like, this is like worst case scenario for any time of day and any time of year.
Okay.
Like this is like the worst that it theoretically should ever be.
So what are your thoughts on EVs after doing this?
Yeah, I was gonna say I haven't always really been a fan of like the EV, not really because of like the battery and like the health hazard. I think it's more kind of like the infrastructure and how fast they kind of like deplete, because we're heavily dependent on like gasoline, and eventually I think gasoline is going to have to kind of go away, and we kind of want to go towards like EV, but the infrastructure isn't there, and that's what we're kind of trying to do with all those different like storages and the EVs. But I just don't think that it's really going to catch on. I think like it wants to. I think something around like hopefully like natural gas or hydrogen kind of like a thing would hopefully be like the next thing, because
Wouldn't hydrogen almost be worse? Isn't that worse on catching fire?
oh, you're talking about
being
like
combustible.
Hindenburg.
I'm just
The
asking
Hindenburg-
questions.
Yeah, there's got to be like a safe way, because I think there's always like I think there's some sort of like there's some gas station in Lincoln that I know of. I can't remember if it was like liquid propane that it ran on, or if it was like hydrogen that it went on. But yeah, there's some other kind of form that is relatively kind of new. But yeah, I think in the future, I really don't see like electric being as dependent as what we would hopefully kind of do, unless we kind of move away from safer materials, because like these are all kind of like lithium battery kind of instances. So unless we find some sort of other storage capacity that's not lithium based, that is actually,
which these batteries take a lot of resources to build too.
Yeah,
the
mine and
yeah, that's what I mean. So we're not. That's what I'll never understand about some of this EV stuff is it's toxic, and
it's not a problem until you find the problems. So like you always think of like all these cool. Yeah, that's the thing. Like you invent something.
People didn't know smoking was bad until everybody started getting cancer.
I know. Just like gasoline, it was leaded and now it's unleaded, stuff like that. So it's always, you find new things, and that's kind of like, you figure out with the scientific community that, you develop these things and like, oh, something is very wrong with it. And then, do you want to fix it, or do people just kind of want to ignore it?
How often does that happen?
Just like ignoring it?
Yeah.
I think
in the scientific community.
Oh, in the scientific community, you don't really ignore it. In a general population sense, I'd say you'd see it's more like ignoring, unless it kind of like happens to you, kind of like a thing.
Gotcha.
Because I always love to do like the Men in Black kind of quote that is in there. So like a person is smart, but people are dumb, panicky, and all that stuff.
That's yeah. I get that. We talk about that all the time on our other podcast. Is that all you got for the EV stuff?
That'd be for like the EV, but like so the next thing is I kind of forgot about. I put in this one. This is the hydrogen chloride, and so like this would be like hydrogen chloric acid if it were to basically react with like water molecules. And so I forget what was the threshold on this one. I think it was like 50,000. So anywhere that's in the orange is bad. So basically, once again, basically within this 100 meters isn't the greatest. And I think here, the low end is, the 1800 for the acute.
And we're still at 10 meters, right? 10 meters up.
Yeah, this is like the smokestack at 10 meters.
Yeah.
And so like this is like the stuff that's like falling down.
So could this ever cause acid rain?
It'd be hydrochloric acid. Like that it would react. It wouldn't be like sulfuric acid and stuff like that. It's hydrochloric acid.
Okay. I just didn't know if it would ever mix up in the atmosphere and cause any kind of
that kind of like short term kind of thing. I don't believe so. You're at that point you're kind of thinking of like coal plants and like volcanoes that you need like a large scale.
I'm just asking questions.
Yeah, so something short like this probably wouldn't say, you'd have like kind of like an acid rain kind of like event. And so the next thing was the power wall. So here's like the cool thing that, I was able to do. So, you take this screenshot, you model it, this house. And so like this like white star is the power wall. And here's like the roof line. And so here's this other house. And so you're basically saying like, given all the weather parameters, what is it going to be? And so in this case, we basically move this data back to where our source was. So that way we didn't have to like run a new whole simulation. And so with the power wall, we actually find that it's actually, relatively, I guess, safe. I wouldn't really say safe at this point. Because at this point, as far as like a hazardous material stuff that you're breathing in, it's not as bad as what it could be. But otherwise, at that point, let's say your power wall is on fire and you're not really worried about the breathing and stuff. You're worried more about your house that's catching on fire, your neighbor's house that more than likely might be catching on fire.
Yep.
And so the other thing that we were kind of asked to measure is how much of this material is being deposited on the on the surface. So you can see with this plastic material that's actually being deposited, it's actually relatively small, and so it's microgram per like meter cubed. And so when we say, or not microgram. So not microgram, milligram per meter squared. So if you were to think of like a milligram, it's basically like a grain of sand is 1 milligram. So this stuff weighs less than like a grain of sand. That's basically how much is being like basically deposited back onto Earth. So that's basically the dry deposition and wet deposition. That's total deposition at that point. And so that's basically all there is for like this battery fire.
That's crazy. That's crazy. So at the end of the day, EVs, no.
I wouldn't really trust mine. I was kind of like a fan like the beginning, but then you model this kind of stuff, and you kind of see how dangerous this is because it's just a giant battery on wheels.
Right.
As what is all it is.
Right. Dang.
And so, as much as these things cost and the materials that it kind of does, but I mean, like I said, we're modeling this thing to emit for like 2 some hours, and so it's not like you're going to be there for like the 2 some hours.
Right.
But it's just kind of like these hazardous materials that are kind of being in there, and you don't know how people are abusing these batteries.
Yeah, that too, right?
Yeah.
Yeah. That's interesting. Well, we'll probably wrap it up there. That's all right with you.
Yeah, that's fine. Otherwise, because otherwise I still had the Mexican energy generating units or the Texas PM 2.5, but those.
Can you just briefly explain kind of what are those just as hazardous or?
Oh, the Mexican EGU one was basically saying like this is with TCQ, and so like they're kind of concerned that there is a new, I think, oil plant that was going up, and how it's going to affect like their 8-hour ozone deal. And so we put that simulation in there again with that ski chem stuff and was able to model it. And what we found is, it basically underrepresents what like a background data. So it's underestimating what it should be. So that kind of goes back with that verification kind of stuff. So with that, it's underestimating what it should be. As far as like the TCQ PM 2.5 stuff, that's basically kind of like identifying sources of PM 2.5 for TCQ, like where they come from. Can I identify diesel exhaust? Can I identify a dust storm or agricultural stuff? And because TCQ has like all these sensors across the road that can measure if it's diesel exhaust and stuff like that.
Really?
And,
That's interesting. We can measure all that stuff, so we can know if it's diesel or if it's a EV on fire. Or
so if I were to even just kind of like go through, if I just go through this like really quick, it's down here at the very end. So this is where it kind of gets into. So we can say what it is. So here we were basically saying the average PM 2.5. We break this down into local, regional, and multi-regional anomalies. So like this, you can see these spikes here for like this regional, and we can see that this is agricultural burning contributions. So let's say like a farmer has like some sort of fire doing like tires and stuff like that they're burning out there. With the multi-regional, here we want to classify it. So this is like soil and dust, but then here at the local level, we see this diesel exhaust with these peaks here. And then you can see it here at this another station here with the local anomaly where you're having, diesel exhaust contributions. The multi-regional, you're having dust, and the regional, you're having agricultural burning. So that's just a kind of like quick thing on that.
That's wild. I hate to cut you short, but we're getting at that 2.5 hour mark. We've been trying to keep these a little shorter.
We haven't had a 2-hour one for a while.
It's been a while.
Well, because I think even the one that I did like last year, that was like 3 hours, and it was like, how did I do this?
So
for
we
like
started
3
out
hours?
doing long ones, and then I'm like, people have seemed to enjoy the not short, but like hour and a half, 2 hours ish time frame.
Ah,
So again, I'm not trying to cut you short. Just trying to keep people like TikTok, 30-second videos.
I mean, it's more information that we can just keep doing more times than once.
Yeah, we can go back into those another time. And I know you enjoy coming on here. So
I was gonna say, even my kids' like attention span is just like,
well, it's short.
microseconds.
Even our attention span is short. Like, don't get me wrong at all. Don't get me wrong. But maybe next, we'll have to have you on again. We'll go through the last couple studies, and then we'll go through like what we normally do. I know we kind of rehashed kind of what we were talking about last time, so that's probably why it kind of took a little longer than we maybe
yeah, because you
expected.
can actually see the pictures. I probably spent a lot more time on the machine learning than what I should have.
It's okay. It's all right. You love it.
Yeah.
I'm interested. It's all good. I'm sure our viewers will enjoy it.
I know, like, so I know we just got like another study here for another battery thing that started yesterday, I believe. So like it'll be like another like huge container, huge IDL case. What's another one that we're, like I said, we're doing the war stuff with TCQ, the one satellite one that I don't really care about with the one lady.
You got a lot going on, huh?
There's the hail stuff that we'll be doing later in the year. So yeah.
Well, maybe in the summertime we'll have to bring you back on too and go through the pivotal weather and actually see some storms. Maybe when we have some storms and walk through, you can show some of that stuff.
Yeah, that's fine. Yeah, because what? It would have to be like a storm that would be occurring like, that afternoon, so like a day in advance or something.
Yeah, a day in advance or go whatever you.
We don't
you'd
even
let
need to see the storm, but at least we'd see it in practice.
Or just
show
take
us
The website in practice more
instead of seeing just blank.
because it's
You know
winter.
what I mean? Because it's wintertime.
either that or just take Zach and you out to, out on a trip and go storm
There you
chasing.
Go vlog.
I did that one that day that
You did.
he went down. I drove around that whole time. That was the one that had like the 3 storms. I just kind of kept driving between the storms and staying up high so I could see what shit was going on. Because that's fun to me. I don't like in the middle of the day being inside. It bothers me.
So like
Freaks me out.
I know like Oklahoma, I think they're just trying to get a law passed where you have to have like a storm chaser license to go chase storms.
What?
How are they going to prove you're chasing
Yeah,
storms?
right?
I'm just out driving
I'm
around. What are you
driving.
talking about?
Can't stop me from driving.
Yeah, that's
Yeah, so
interesting.
it's mostly like if the people like kind of like blocked off the area, so like it's already been like disaster ridden.
yeah.
People are going out there with like their drones or
Yeah,
doing
it's
like
maybe
those
too much at
vlogging
that point.
and just kind of like, oh, look at this guy's house that just got destroyed.
Yeah. Yeah, that seems a little. I'm not into that. I just like when it's happening. Like, it's exhilarating at times.
Definitely. We're actually going to have a storm chaser on here soon. One around here that does it. Yeah, I think he's from Battle Creek. Actually, I showed it. I sent it to you.
Oh, you might have.
Yeah.
I forgot.
I don't remember his name though.
Yeah, I think like the National Weather Service, they put on like these free clinics at like the Northeast Egg
Oh,
Bed,
really?
I believe, whatever.
Hmm.
I can't remember. I think Norfolk is either late February or early March is like when
Interesting.
they do theirs.
One of my classmates does that. He goes every year and he goes through those classes.
Oh, really?
Yeah.
That's cool.
I don't know what they do. Like, I just know I've seen him
I had to
post on
teach those
Facebook or
classes.
whatever. You do it?
Well, I had to teach them when I did the
yeah.
internship at the National Weather Service. I would go on these
To be a
different.
trained spotter or something? Isn't that what it's for? You're just all it is to be a
you
tornado
learn.
spotter.
Yeah, you learn like all the different like cues and like different clouds. Like, is this like a funnel cloud or is
Yeah.
this what is this kind of cloud?
Just to help, like, that way that you guys, when you're doing your data, you have good data points to call back on.
Yeah, so like like I know there's like one guy that sits out by I think Lincoln Northeast or Lutheran High Northeast. Like there's this guy up there on the hill. I'll see him out there just looking for storms, and they basically put out like a APB and says activate spotters and go to your positions or whatever and go monitor and say, and you'll call in and say hey, my name is Chase, storm spotter, and I'm at this point. I can see a funnel cloud from, this location. And then that way, because when you look at like the radar that on your phone,
Yeah.
like if we were to pull up like radar scope is what I use for like radar.
Mm-hmm.
You can look at like the reflectivity, you can look at the velocity, but when you do it here in Norfolk, that beam is like 6,000 feet up in the air. It's not. So you're seeing the radar as it's like really high up,
Right.
and so like it kind of gets hard for like the National Weather Service when it's further away from the beam. But I know they have like classes where they go down to like storm. They like the SPC and they do like all these trainings to like do warnings and stuff like that.
Mm-hmm. That's wild. Well, we'll have to have you back on. Interesting stuff that you got.
It always is.
Just takes a long time to explain, which is fine. All good. Well, huge thanks for you coming, though.
Yeah.
We
no
always
problem.
appreciate you having on. We'll have to start a little weather thing. We'll have to get you like a camera and you can do a little brief weather show during the summer.
There you go.
We'll put it on our Facebook page or something.
Yeah, that's fine.
Let people know what's going on. Well, huge thanks to my co-host Vance Nidek. Without him, the show would not be what it is. Huge thanks to Chase Calkins for making time to come. We really appreciate you making time for beer today.
Yeah, no problem.
Awesome.
Thank you.
Perfect. Keep on the lookout for more great episodes. We'll see you guys next week.